There is a place in space where the laws of physics as we understand them simply stop working. Not break down in some minor or technical sense, not fail to give precise predictions, not require a small correction, not produce an answer that is slightly off from what experiment confirms. Stop working entirely. Reach a point where the equations that have described every other phenomenon in the universe with extraordinary precision arrive at a result that is not merely wrong but meaningless. An infinity, a division by zero, a singularity, a place where the mathematics itself collapses and falls silent. That place is called a black hole, and there are, by current estimates, approximately 40 million of them in our galaxy alone. 40 million objects, each so massive, each so thoroughly collapsed upon itself, each generating gravity so intense that not even light can escape. Each one a place where space and time behave in ways that have no analogy in ordinary experience, where our deepest theories of physics reach their limits, where something is happening that we cannot fully describe or fully imagine. They range from the remnants of massive stars that collapsed at the ends of their lives, objects perhaps 10 times the mass of our Sun compressed into a sphere perhaps 30 kilometers across, to the supermassive objects that sit at the centers of galaxies, objects millions or billions of times the mass of the Sun, whose influence shapes the structure of the galaxy around them. They have been detected by the distortions they produce in the paths of nearby stars, by the gravitational waves they produce when they collide with each other, and finally, in 2019, by the first direct image of one, the shadow of the supermassive black hole at the center of a galaxy called M87, 55 million light-years away, its silhouette captured by a network of radio telescopes spread across the entire Earth, working together as a single instrument. And yet, for all that we have detected them, for all the extraordinary effort that has gone into the science of black holes over the past century, they remain among the most mysterious objects in the universe. The question of what happens inside them, what is at the singularity at their center, whether information that falls into them is truly lost, what their ultimate fate is over the lifetime of the universe. These questions are among the deepest open problems in all of physics. They sit at the intersection of the two greatest theories of the 20th century, general relativity and quantum mechanics, and the fact that those two theories give incompatible answers when applied to the interior of a black hole is not a minor technical problem to be cleaned up at the edges. It is a fundamental indication that our understanding of nature is incomplete in some deep way that has not yet been resolved. This is the story of black holes, their discovery, their physics, their strangeness, and the profound questions they raise about the nature of space, time, and information. It is a story about what happens when gravity wins. The concept of an object so massive that light cannot escape from it was first proposed not by a physicist of the 20th century, but by an English clergyman and amateur scientist named John Michell in a paper presented to the Royal Society in 1783. Michell was thinking about the nature of stars and gravity in the framework of Newtonian mechanics, and he posed a straightforward question. If light has a finite speed, and if light is affected by gravity, could an object be massive enough that the escape velocity from its surface exceeds the speed of light? Escape velocity is the speed that an object must reach to escape the gravitational pull of a body and travel off to infinity without being pulled back. For the Earth, the escape velocity is approximately 11 kilometers per second. A rocket must reach this speed to leave the Earth entirely. For the Sun, the escape velocity is about 617 kilometers per second. For denser and more massive objects, the escape velocity is higher. Michell calculated that if a star were sufficiently dense, specifically if its radius was small enough relative to its mass, the escape velocity from its surface would exceed the speed of light. Light emitted from such a star would be pulled back by gravity before it could travel away, and the star would be invisible to any outside observer. Michel called these hypothetical objects dark stars, and he proposed that they might be detectable not by their own light, which could not escape, but by the gravitational influence they exerted on other stars that might orbit them. This is a remarkably prescient observation. One of the primary modern methods for detecting black holes is precisely this indirect method, observing the behavior of matter and light near them rather than the black holes themselves. Michel's paper attracted little attention at the time. A similar calculation was independently made by the French mathematician Pierre-Simon Laplace in 1796, and then largely forgotten when the wave theory of light became dominant in the early 19th century. The wave theory made it unclear whether light, understood as a wave rather than a particle, would be affected by gravity at all, and the concept of dark stars fell into dormancy for more than a century. It was revived, transformed, and placed on an entirely new conceptual foundation by Albert Einstein's General Theory of Relativity, published in 1915. General relativity is one of the most beautiful and one of the most strange theories in the history of science. Its central idea is that gravity is not a force in the Newtonian sense, not an invisible influence transmitted instantaneously across empty space between massive objects, but a curvature of space-time itself, produced by the presence of mass and energy. Matter tells space-time how to curve, and curved space-time tells matter how to move. The idea requires a moment to sit with, because it is genuinely different from the everyday experience of gravity as a pulling force. In general relativity, the Earth is not pulling you toward it as you sit or lie wherever you are right now. Rather, the mass of the Earth has curved the space-time around it, and you are following the straightest possible path through that curved space-time. And in curved space-time, the straightest possible path curves toward the Earth. What feels like a force pulling you down is, in Einstein's description, the geometry of space-time itself. The equations of general relativity, the Einstein field equations, are among the most elegant and the most computationally challenging equations in all of physics. They relate the curvature of space-time at every point to the distribution of mass and energy at that point in a set of 10 coupled non-linear partial differential equations. Finding exact solutions to these equations is generally very difficult, and Einstein himself initially found only approximate solutions for simple cases. He was not certain whether exact solutions even existed. In 1916, within months of Einstein publishing the General Theory of Relativity, a German physicist and astronomer named Karl Schwarzschild found an exact solution. Schwarzschild was serving on the Eastern Front in the First World War when he read Einstein's papers, and he found the time, in the intervals between artillery calculations, to work out the exact solution for the simplest possible case: the geometry of space-time outside a perfectly spherical, non-rotating, electrically neutral mass. He sent his solution to Einstein from the front, and Einstein presented it to the Prussian Academy of Sciences. Schwarzschild died a few months later from a disease contracted at the front, never knowing how profoundly his solution would shape the subsequent century of physics. The Schwarzschild solution describes the space-time geometry outside a spherical mass, and for most purposes, it gives results that are essentially identical to Newtonian gravity: the orbits of planets, the deflection of light, the precession of Mercury's perihelion, all of the phenomena that general relativity was initially tested on. But when you look closely at the mathematical structure of the Schwarzschild solution, something strange appears. At a specific distance from the center of any mass, a distance that depends only on the mass and is now called the Schwarzschild radius, the mathematics of the solution behaves peculiarly. The factor that describes the warping of time becomes zero, and the factor that describes the warping of space becomes infinite. For ordinary objects like the Earth or the Sun, The Schwarzschild radius is far smaller than the physical size of the object itself. The Schwarzschild radius of the Earth is about 9 millimeters, deep in the interior of the planet. The peculiar behavior of the Schwarzschild solution at the Schwarzschild radius only matters if an object is compressed to a smaller radius than its Schwarzschild radius, if all its mass is concentrated inside that tiny critical sphere. What happens then? For years, physicists disagreed about whether the peculiar behavior at the Schwarzschild radius represented a genuine physical phenomenon or simply a failure of the coordinate system being used to describe the spacetime, a mathematical artifact rather than a physical reality. Einstein himself believed until late in his life that nature would prevent any object from being compressed to such extreme densities, that some physical mechanism would always intervene before a mass was compressed inside its Schwarzschild radius. He was wrong. Nature provides no such protection. The first indication that nature does not prevent the formation of black holes came from a calculation performed in 1939 by J. Robert Oppenheimer and his student Hartland Snyder, just months before Oppenheimer would become the scientific director of the Manhattan Project. Oppenheimer and Snyder studied the gravitational collapse of a massive star. What happens when a star so massive that no known pressure can support it against gravity collapses under its own weight? They found that for a sufficiently massive collapsing star, the collapse does not stop. There is no equilibrium configuration that the star can reach. The material of the star simply falls inward, past the Schwarzschild radius, and keeps falling. The mathematics of what happens inside the Schwarzschild radius, what the geometry of space-time looks like there, what happens to the matter that falls in, was murky in their 1939 treatment, partly because of the coordinates they were using, and partly because they were using only classical general relativity without quantum mechanics. But the key result was clear. If a star is massive enough, gravity wins. There is no final state of supported, stable matter. The collapse continues. The paper was published on September 1st, 1939, the same day Germany invaded Poland and the Second World War began. It attracted almost no attention. Oppenheimer moved on to other things. For the next 2 decades, the implications of the Oppenheimer-Snyder calculation remained largely unexplored. It was during this period that the physicist John Wheeler, who would later coin the term underscore, quote underscore, 0 underscore, began to think seriously about the objects that extreme gravitational collapse produced. Wheeler was initially skeptical, as Einstein had been, that nature really allowed such extreme objects to exist. He worked to find mechanisms that might prevent complete collapse. Gradually, through the 1950s, he came to accept that no such mechanism existed, and his group at Princeton became one of the centers of the developing field of what was then called relativistic astrophysics. In 1967, at a conference in New York, Wheeler used the term quote 1 for the first time to describe a gravitationally collapsed object from which nothing can escape. The term was vivid, memorable, and slightly ominous in a way that immediately stuck. It replaced the more technical and less evocative terms that had been used before, quote 2 and quote 3 and quote 4, and the new name helped bring the concept into broader scientific and public consciousness. A field that had been an esoteric backwater of general relativity theory began to attract serious attention. To understand what a black hole actually is, not as a mathematical abstraction, but as a physical object, it helps to start with how one forms. The most common type of black hole is the stellar mass black hole, formed from the death of a very massive star. To understand this, you need to know something about how stars work. A star is, at the most basic level, a contest between gravity and pressure. The mass of the star generates gravity that pulls everything toward the center. The energy produced by nuclear fusion in the star's core generates pressure, heat and radiation pressure, that pushes outward against gravity. For most of a star's life, these two forces are in balance. The star is a stable, long-lived object precisely because gravity and pressure are in equilibrium. But this equilibrium depends on the nuclear fuel in the star's core. Hydrogen fuses into helium, releasing energy. When the hydrogen runs out, helium fuses into carbon and oxygen. When the helium runs out, carbon and oxygen fuse into heavier elements. The sequence continues up the periodic table: neon, magnesium, silicon, sulfur. Each successive fuel burning faster and releasing less energy per reaction, the star consuming millions of years of hydrogen fuel in its main sequence lifetime, then thousands of years of helium fuel, then hundreds of years of carbon fuel, then just a year of silicon fuel in a frantic acceleration toward the end. At the end of this sequence lies iron. Iron is the most stable atomic nucleus. It is the endpoint of nuclear fusion, the element at which the fusion process no longer releases energy but instead requires it. When the core of a massive star fills with iron, fusion stops. The pressure that has supported the star against gravity for millions of years vanishes in a fraction of a second. What follows is one of the most violent events in the universe. Without the outward pressure of fusion energy, the iron core collapses. It collapses with extraordinary speed, from the size of the Earth to the size of a city in less than a second. The outer layers of the star, which have been supported by the core, lose their support and fall inward as well, crashing onto the collapsing core at a significant fraction of the speed of light. The collision of the infalling outer layers with the now rebounding core produces a shock wave that tears the star apart from the inside. A supernova explosion of staggering violence, releasing more energy in a few seconds than the Sun will release in its entire 10 billion year lifetime, briefly outshining the entire galaxy in which it occurs. What remains at the center, if the original star was massive enough, is the collapsed core, now compressed to extraordinary density by the force of the collapse. For stars whose core is above approximately 3 times the mass of the Sun at the moment of collapse, no known force can stop the compression, not the pressure of electrons being forced together that supports white dwarfs, the remnants of less massive stars, not the pressure of neutrons being forced together that supports neutron stars, the remnants of moderately massive stars, where a city-sized object can contain more mass than the Sun. For the most massive stars, even neutron degeneracy pressure is overcome by gravity. The collapse continues past the neutron star stage, past the point where our equations tell us a neutron star would form, into the regime where our equations give meaningless results, into a black hole. The boundary of a black hole, the surface that separates the region from which escape is possible from the region from which escape is not, is called the event horizon. It is named for the horizon of experience. As a ship disappears over the ocean horizon, it passes beyond the boundary of what you can see. The event horizon of a black hole is the boundary beyond which no information, no light, no matter, no signal of any kind can ever reach the outside universe. The event horizon is not a physical surface. There is no wall, no membrane, no visible boundary at the event horizon. If you were falling toward a black hole, a stellar mass black hole, not one of the supermassive ones at galactic centers, you would not notice anything unusual as you cross the event horizon. The local conditions, the tidal forces, the density of matter, the intensity of radiation would be unremarkable at the moment of crossing. You would simply continue falling. The difference is that after you cross the event horizon, you could not send a signal back to the outside universe. You could not escape. Every path available to you, every possible direction you could travel at every possible speed, including the speed of light, would lead you deeper into the black hole rather than back out. This is the essential physics of the event horizon, and it is deeply counterintuitive. The event horizon is not a place where gravity is unbearably strong. For a sufficiently massive black hole, the gravitational acceleration at the event horizon is actually quite modest. It is a place where the geometry of space-time has been so severely distorted by the enclosed mass that all directions in space-time, all possible futures, point inward rather than outward. Time itself is affected. Far from a black hole, time runs normally. As you approach the event horizon from outside, time appears to slow, not from your own perspective, but as observed by someone watching you from a safe distance. An outside observer watching you fall toward a black hole would see your fall slow progressively as you approach the event horizon, with your image becoming increasingly redshifted as the photons you emit have to climb out of an increasingly deep gravitational well to reach the observer. From the outside observer's perspective, you would appear to freeze at the event horizon, your image growing dimmer and more red as the photons from your position take longer and longer to escape. You would never appear to cross the event horizon from their perspective. From your own perspective, falling freely, you would experience no slowing of time and would cross the event horizon without fanfare, in finite proper time. The discrepancy between what the outside observer sees and what you experience is one of the most striking consequences of general relativity, and it illustrates something profound about the nature of time and simultaneity. There is no absolute observer-independent fact about when you cross the event horizon. From outside, you never do. From inside, you already have. At the center of a black hole, at least in the classical general relativity picture, lies the singularity. The singularity is the point, or region, where the density becomes infinite, where space-time curvature becomes infinite, where the equations of general relativity break down entirely and give no meaningful predictions. It is not a place in the ordinary sense. In a Schwarzschild black hole, it is more accurately described as a moment in time, a moment in the future of everything that falls past the event horizon, unavoidable in the same way that tomorrow is unavoidable for you. Everything that falls into a black hole reaches the singularity in finite proper time and is, in the classical picture, crushed to infinite density. The word underscore underscore, quote underscore 5 underscore underscore is not quite right, but it conveys the essential quality. At the singularity, the physical description of matter and space-time that we possess, built on the framework of quantum mechanics and general relativity, simply fails. We do not know what happens there because our theories are not adequate to describe it. This is not merely a gap in knowledge that more careful calculation can fill. The incompatibility between general relativity and quantum mechanics at the conditions of the singularity is a fundamental problem in theoretical physics. General relativity is a classical theory. It describes the universe in terms of smooth, continuous fields and the smooth, continuous curvature of space-time. Quantum mechanics is, at its core, a theory of discreteness, of energy levels, of quanta, of irreducible uncertainty. At ordinary energies and scales, these two frameworks can be applied separately to different domains without conflict, but at the extreme conditions of a black hole singularity, at the Planck scale, where the density is so high and the scale so small that quantum effects and gravitational effects are both equally important, the two theories give incompatible answers, and neither can be trusted. The resolution of this incompatibility requires a theory of quantum gravity, a theory that successfully combines the principles of quantum mechanics with the description of space-time curvature from general relativity. The development of such a theory is arguably the central unsolved problem of theoretical physics. String theory and loop quantum gravity are the two most developed candidate frameworks, but neither has produced a complete, consistent, and empirically confirmed theory of quantum gravity. Until one does, the physics of the black hole singularity remains genuinely unknown. The existence of black holes moved from theoretical prediction to observational reality through a series of discoveries across the latter half of the 20th century. In 1963, the astronomer Martin Schmidt was studying the spectrum of a faint object designated 3C273, which had been catalogued as a star-like object but whose spectrum did not match any known stellar spectrum. Schmidt realized that the strange spectrum could be explained if the object was not a star in our galaxy at all, but an enormously luminous object at an enormous distance, so far away that the expansion of the universe had stretched its light to longer wavelengths, shifting familiar spectral features far into the red end of the spectrum. Calculating the distance implied by the redshift, Schmidt found that 3C273 was approximately 2 billion light-years away, and that to be visible at that distance, it must be radiating energy at a rate equivalent to the simultaneous explosion of trillions of suns. The object was called a quasar, a contraction of quasi-stellar radio source, and the power source for its extraordinary luminosity was quickly identified as a supermassive black hole at its center. As gas and dust fell into the black hole, drawn in by its immense gravity from the surrounding galaxy, it formed a flattened, spinning disk of material called an accretion disk. And as the material in this disk was compressed and heated by friction and gravitational energy, it radiated at extraordinary luminosity. A fraction of the mass energy of the infalling material, several percent, compared to the fraction of a percent that nuclear fusion releases, was converted into radiation. The most efficient energy generator in the universe is not a nuclear reactor or a fusion bomb, but a black hole surrounded by an accretion disk. The discovery of quasars demonstrated that supermassive black holes were real, active, and energetic objects, not merely theoretical curiosities, but the power sources for some of the most luminous objects in the observable universe. The subsequent decades brought the discovery of active galactic nuclei, the realization that essentially all large galaxies contain supermassive black holes at their centers, and the gradual accumulation of evidence that these supermassive black holes played a central role in the formation and evolution of the galaxies around them. The evidence for stellar mass black holes accumulated through a different route: X-ray astronomy. In the 1970s, satellites equipped with X-ray detectors discovered point sources of intense X-ray emission in our galaxy that were subsequently identified as binary star systems, pairs of stars orbiting each other, in which one member of the pair was a compact object drawing in gas from its companion. The X-rays came from the accretion disk around the compact object, heated to tens of millions of degrees by the energy of infalling material. In many of these systems, the mass of the compact object, determined from the orbital dynamics of the binary, exceeded the maximum mass that a neutron star could have, leaving a black hole as the only viable explanation. By the end of the 20th century, the existence of black holes was no longer seriously in doubt. The question had moved from whether they existed to what they were like, what happened inside them, what their ultimate fate was, what they implied about the fundamental nature of space, time, and information. That question remains, in its deepest form, unanswered. In the early 1970s, a young physicist named Stephen Hawking made a discovery that transformed the understanding of black holes and created one of the deepest paradoxes in all of theoretical physics. Hawking was studying black holes using the newly developed techniques of quantum field theory in curved space-time, the application of quantum mechanics not to flat, featureless space, but to the curved space-time of general relativity. He was trying to understand what quantum effects would do near the event horizon of a black hole, where the curvature of space-time was severe. What he found astonished him, and has astonished everyone who has thought carefully about it since. He found that black holes are not black, not completely, not when quantum effects are taken into account. Quantum mechanics implies that the vacuum of space, even empty space, containing nothing, is filled with a constant flux of virtual particle-antiparticle pairs popping into existence and annihilating again, borrowing energy from the vacuum for brief intervals allowed by the uncertainty principle. Near the event horizon of a black hole, something strange happens to these virtual pairs. Occasionally, one member of the pair falls across the event horizon while the other escapes to infinity. When this happens, the pair cannot annihilate. They are permanently separated by the horizon. The escaping particle carries energy away from the black hole, and the black hole loses mass to compensate. From the perspective of a distant observer, the black hole appears to be emitting a steady flux of thermal radiation, as if it were a hot object radiating heat. This radiation is called Hawking radiation, and its temperature is inversely proportional to the mass of the black hole. A stellar mass black hole radiates at a temperature far below even the cosmic microwave background, making the Hawking radiation from real black holes undetectable with any current technology. But in principle, if a black hole were to persist long enough, and if nothing were falling into it, it would lose mass through Hawking radiation, shrinking progressively as it lost energy, its temperature rising as it lost mass, until in the final moments it would flare in an explosion of particles and radiation, completely evaporating. The discovery of Hawking radiation was a triumph, a demonstration that quantum mechanics and general relativity could be combined, at least in this semi-classical approximation, to produce new physical predictions. But it also immediately raised a problem that has not been resolved in the 50 years since Hawking made his discovery, a problem that physicists call the black hole information paradox. The matter that falls into a black hole carries information, the specific quantum states of the particles, their positions and momenta and spins, all the physical details that characterize their state. If the black hole eventually evaporates entirely through Hawking radiation, what becomes of that information? The Hawking radiation, as calculated in the original framework, is completely thermal, completely random, containing no information about what fell in. If a book and a diamond and a human being all fell into a black hole, and the black hole eventually evaporated, the radiation coming out would be the same regardless of what went in. The information in the book, the structure of the diamond, the specific configuration of atoms that constituted the person, all of it would be lost. This would violate one of the most fundamental principles of quantum mechanics, that information is conserved, that the evolution of a quantum state is reversible, that no physical process can truly destroy information. If Hawking's calculation is correct, black holes violate this principle. They are information destroyers. They take in ordered, information-rich states and emit disordered, information-free thermal radiation. The question of whether information is truly lost in black holes, or whether it somehow escapes in the Hawking radiation, encoded in correlations too subtle for the original calculation to capture, is the black hole information paradox, and it is one of the most intensely debated open questions in theoretical physics. On one side stand those who believe that quantum mechanics is fundamental and unbreakable, and that therefore information must somehow escape from black holes, even if we do not yet understand how. On the other side have stood those who believe that general relativity is fundamental, and that the event horizon truly imprisons information. The debate has been ongoing for 50 years. It has generated some of the most creative and the most technically demanding theoretical work in the history of physics. And it has not been resolved. It is, in the most literal sense, an open question at the edge of human understanding. A place where our best theories of the universe are in genuine conflict with each other, and where the resolution, when it comes, will require ideas that no one has fully formulated yet. In the darkness at the center of a black hole, in the silent collapse past the event horizon, in the quantum fluctuations that slowly consume the mass of the most extreme objects in the universe, something is happening that physics does not yet fully understand. The universe keeps its deepest secrets in the darkest places. The information paradox that Hawking's 1974 calculation produced did not sit quietly in the physics literature. It spread and it grew, and it attracted some of the most brilliant minds of the late 20th and early 21st century, each attempting to understand whether black holes truly destroy information, or whether the information escapes in some form that Hawking's calculation had missed. The debate was not merely technical, it was foundational, because it concerned the most basic principles of quantum mechanics and their relationship to the geometry of space-time. If information could be lost in black holes, then quantum mechanics as currently formulated was not the complete description of physical reality that physicists believed it to be. Something would need to change. The person who felt this most acutely was not Hawking himself, who initially accepted that information was lost and thought this was simply a new feature of the universe that physics would have to accommodate. The person who felt it most acutely was John Preskill, a theoretical physicist at Caltech, who was among the most careful thinkers about the foundations of quantum mechanics in his generation. Preskill argued insistently through the 1980s and 1990s that information loss in black holes was impossible, that quantum mechanics was simply too fundamental a principle to be violated, and that however strange the resolution of the paradox turned out to be, information had to escape somehow. In 1997, Preskill made a famous bet with Hawking and the physicist Kip Thorne. Preskill wagered that information was preserved. Hawking and Thorne wagered that it was lost. The stakes were an encyclopedia of the winner's choice. The bet attracted enormous attention in the physics community, partly for its specific terms and partly because it crystallized the central dispute in black hole physics in a form that was memorable and human. The bet stood for 7 years. The theorist who began to tip the balance was not primarily a black hole physicist, but a string theorist, a practitioner of the framework that attempts to unify all of physics by describing the fundamental constituents of matter as tiny vibrating strings rather than point particles. String theory is a vast and technically demanding subject, and its relationship to observable physics has been contested for decades. But in 1997, the Argentine-American physicist Juan Maldacena made a discovery within string theory that, while not directly about black holes, had implications for the information paradox that proved to be transformative. Maldacena's discovery is called the ADS/CFT correspondence, or more colloquially, the holographic principle. It is one of the most remarkable and most cited results in theoretical physics of the past 30 years, and its full implications are still being worked out. In its essential form, it states that a theory of gravity in a particular kind of curved space-time, an anti-de Sitter space, or ADS, is exactly equivalent to a quantum field theory without gravity living on the lower dimensional boundary of that space-time. The 5-dimensional gravitational theory in the interior of the ADS space is, in a precise mathematical sense, equivalent to a 4-dimensional quantum field theory on its boundary. The two descriptions encode the same physics, just in very different ways. The phrase holographic principle is used because this equivalence is reminiscent of a hologram, a 2-dimensional surface that encodes all the information needed to reconstruct a 3-dimensional image. In the ADS/CFT correspondence, the higher dimensional gravitational physics of the interior is entirely encoded in the lower dimensional quantum field theory of the boundary. All the information that seems to exist in 3 dimensions is really encoded on a 2-dimensional surface. The implication for the information paradox is profound. If the physics of a black hole in the ADS interior is equivalent to a quantum field theory on the boundary, and if quantum field theories manifestly preserve information because they are quantum mechanical systems evolving unitarily according to the Schrödinger equation without any information loss, then the black hole physics must also preserve information. The ADS/CFT correspondence, if correct, implies that information is not lost in black holes because the corresponding boundary description, which contains the same physics, preserves it. This is not a direct calculation of how the information escapes. Maldaceno's result does not tell you the specific mechanism by which the information encoded in the infalling matter reappears in the Hawking radiation. But it provides a powerful argument that it must escape somehow because the dual description is unitary. The information paradox in the ADS/CFT framework is not a paradox about whether information is lost. It is a puzzle about the mechanism of information escape that remains to be understood. In 2004, Hawking conceded. He announced at a conference in Dublin that he had changed his mind about information loss, accepting the argument from ADS/CFT that information was preserved. He paid his bet to Preskill, an encyclopedia, as agreed. Thorne, notably, did not concede at the same time. He later accepted the consensus, but more gradually and with more reservation. The community mostly followed Hawking's lead, and though the specific mechanism of information escape remained, and remains, deeply unclear. The search for the mechanism of information escape led to one of the most provocative and most technically demanding ideas in recent theoretical physics: the firewall. The firewall controversy began in 2012 with a paper by Ahmed Al-Mahiri, Donald Marolf, Joseph Polchinski, and James Sully, known by their initials as AMPS. They analysed what the preservation of information implied for the experience of an observer falling into a black hole, and they found something deeply troubling. The standard picture of black hole physics, the picture that had prevailed since Hawking's original work, had two central assumptions. First, that an observer falling freely through the event horizon would not notice anything unusual at the moment of crossing. The equivalence principle of general relativity, the cornerstone of Einstein's theory, implied that freely falling observers in a gravitational field should experience the same physics as observers in empty space, at least locally. The event horizon, being a smooth region of space-time in classical general relativity, should not be locally detectable. Second, that the Hawking radiation eventually emitted by the black hole was in a highly entangled quantum state with the matter that had fallen in, that somehow, through a mechanism yet to be understood, the information about the infalling matter was encoded in the emitted radiation. AMPS showed that these two assumptions were mutually inconsistent. If the Hawking radiation is truly entangled with the infalling matter in the way required by unitarity and information preservation, then the region near the event horizon cannot be the smooth, featureless region that the equivalence principle requires. The entanglement structure needed for information preservation is incompatible with the entanglement structure needed for a smooth horizon. Something has to give. Either the equivalence principle is violated at the event horizon, or information is lost. If the equivalence principle is violated at the event horizon, then an observer falling freely through the horizon would not experience a smooth crossing into the black hole's interior. Instead, they would encounter a wall of high-energy radiation, a firewall, at the moment of crossing the horizon, which would destroy them instantaneously. The featureless, unnoticeable crossing that general relativity predicted would be replaced by instant incineration. The firewall argument was received with a mixture of fascination and alarm. It threatened some of the most fundamental principles of general relativity, and it suggested that the resolution of the information paradox required something far more radical than any previously proposed mechanism. The debate it sparked, known as the firewall controversy, generated an enormous amount of theoretical work and has not been conclusively resolved. Various responses to the AMPS argument have been proposed. Some physicists accept the firewall and attempt to understand what it means for the structure of the theory. Others have proposed modifications to quantum mechanics, modifications to general relativity, or entirely new theoretical frameworks that dissolve the paradox without a firewall. The most dramatic proposals involve revisions to our understanding of space-time itself. The suggestion, associated with Juan Maldacena and Leonard Susskind, that the apparent paradox arises from a misunderstanding of how space-time works near the black hole, and that a correct understanding requires recognizing that the entanglement of quantum systems is related in some deep way to the connectivity of space-time, that entangled particles are, in some sense, connected through space-time in a way that has no classical analogue. This proposal, called ER equals EPR, after the Einstein-Rosen bridge, a geometric structure connecting two distant regions of space-time, and Einstein-Podolsky-Rosen entanglement, the quantum correlation between distant particles, suggests that entanglement and space-time geometry are two aspects of the same thing, and that the information paradox is resolved by recognizing that the interior of the black hole is connected to the exterior through the quantum entanglement of the Hawking radiation with the infalling matter. It is a beautiful and audacious idea, and it is far from being established. The information paradox, 50 years after Hawking first identified it, is still open. The resolution, when it comes, will require ideas about quantum gravity that do not yet exist in complete form. The first image of a black hole was released on April 10, 2019. It showed the shadow of the supermassive black hole at the center of the galaxy, M87, 55 million light-years away. A bright ring of light surrounding a dark central region, the glow of the heated accretion disk visible as the black hole's shadow was cast against it. The image was produced by the Event Horizon Telescope, a global network of radio telescopes that had been linked together to function as a single dish with an effective aperture the size of the Earth. Radio waves, with wavelengths far longer than visible light, can penetrate the clouds of gas and dust that obscure the galactic center from optical telescopes, and the specific wavelength used, 1.3 millimeters, was chosen to maximize the resolution achievable with the Earth-size baseline while minimizing the atmospheric interference that would blur the image. The image matched the predictions of general relativity with remarkable precision. The specific shape of the bright ring, the asymmetry between the brighter and dimmer sides caused by the Doppler boosting of radiation from material moving toward the observer relative to material moving away, was exactly what general relativity predicted for a rotating black hole of the mass inferred from the orbital dynamics of stars near the galactic center. The shadow, the dark region in the center, was the size predicted for a black hole of that mass. The M87 image was followed in 2022 by an image of the supermassive black hole at the center of our own galaxy, Sagittarius A star, approximately 27,000 light-years away, with a mass of approximately 4 million times that of the Sun. Imaging. Sagittarius. A star presented additional challenges compared to M87 because the black hole at the center of our galaxy is much smaller in angular size, and because the material orbiting it moves so much faster, with the orbital period of material near the event horizon being minutes rather than days, that the image flickered and changed during the long observing sessions required to collect enough radio wave data. Sophisticated statistical techniques were required to reconstruct a stable image from the variable data. The image of Sagittarius A star confirmed what decades of careful measurements of stellar orbits near the galactic center had already established. That at the center of our galaxy sits a supermassive black hole, its mass equivalent to 4 million suns, compressed into a region smaller than our solar system. The star closest to the galactic center, designated S2, completes a full orbit of the black hole every 16 years, reaching speeds of approximately 3% of the speed of light at its closest approach, and showing the specific orbital precession predicted by general relativity for a compact mass of that magnitude. The direct imaging of black holes was a culmination of a century of theoretical and observational work. From Schwarzschild's calculation in the trenches of the First World War to the pixel-by-pixel reconstruction of the M87 shadow required 9 months of computing time on dedicated supercomputers, the journey had required advances in theoretical physics, in observational astronomy, in detector technology, in computational power, and in international scientific collaboration that spanned dozens of countries and hundreds of researchers. And yet the image, stunning as it was, showed only the exterior of a black hole. It showed the bright ring of heated gas and the dark shadow cast by the event horizon, but it revealed nothing about the interior, about what lies beyond the horizon, about the nature of the singularity, about how the information paradox is resolved. The most important secrets of the black hole remain inaccessible to any telescope because no signal from beyond the event horizon can reach us. The gravitational wave detection that transformed black hole physics came 3 years before the first image, on September 14, 2015. The Laser Interferometer Gravitational Wave Observatory, LIGO, had been operating in its upgraded configuration for 2 days when its detectors in Hanford, Washington, and Livingston, Louisiana, simultaneously registered a signal. The signal was a chirp, a brief oscillation that rose rapidly in frequency over a fraction of a second before ending, and it had the specific form that general relativity predicted for the gravitational waves produced by 2 merging black holes. Gravitational waves are ripples in the fabric of space-time itself, produced by the acceleration of massive objects. Einstein had predicted them as a consequence of general relativity in 1916, within months of publishing the theory, and had then spent years doubting whether they were truly physical, whether they carried energy and could affect detectors, or whether they were merely a mathematical artifact of the coordinates used to describe space-time. The question was not settled until 1956, when the physicist Richard Feynman devised a simple argument, the __7__ argument, that demonstrated that gravitational waves must carry energy and could, in principle, be detected. It took another 60 years to actually detect one. The LIGO detection of September 14, 2015, designated GW 150914, was produced by the merger of 2 black holes approximately 1.3 billion light-years away, with masses of approximately 36 and 29 times the mass of the Sun, merging to form a single black hole of approximately 62 solar masses. The missing 3 solar masses of energy were radiated away as gravitational waves in the brief moment of the merger. An amount of energy equivalent to 3 times the mass of the Sun radiated entirely in the form of space-time ripples in approximately 1/5 of a second. At the peak of the merger, the power radiated in gravitational waves was approximately 50 times greater than the combined luminosity of all the stars in the observable universe. And the effect of this enormous energy release at the LIGO detectors, 1.3 billion light-years away, was a stretching and squeezing of the distance between the detector mirrors by approximately 1/1000th of the diameter of a proton. A displacement so small that it required the most sensitive measurement apparatus ever constructed by human beings. Interferometers with 4-kilometer arms whose mirrors were isolated from vibration by multiple levels of suspension and whose laser beams were stabilized to extraordinary precision. The detection was announced in February 2016, and it was received with the kind of excitement that the physics community reserves for moments of genuine breakthrough. The Nobel Prize in Physics was awarded the following year to Rainer Weiss, Kip Thorne, and Barry Barish for the detection. Since 2015, more than 90 gravitational wave events have been detected by LIGO and its European counterpart Virgo, the vast majority of them black hole mergers, and the catalogue of confirmed black holes has grown dramatically. Gravitational wave astronomy opened a new window on the universe. The ability to detect events that produce no light, no electromagnetic radiation of any kind, but that shake space-time itself. It confirmed general relativity in the most extreme conditions yet tested, with the observed waveforms matching the theoretical predictions with extraordinary precision. It revealed that black hole mergers were far more common than had been expected, and that the black holes involved covered a surprisingly wide range of masses, including several that were in mass ranges that stellar evolution theory had difficulty explaining, and it raised new questions. Among the most puzzling was the detection, in 2019, of a merger involving an object of approximately 2.6 solar masses, too massive to be a neutron star by standard estimates, but in the mass range that stellar evolution theory suggests should not produce black holes, a gap between the maximum neutron star mass and the minimum black hole mass. Whether this object was a very massive neutron star, or a very light black hole, or something else entirely, is not yet established. The universe, as gravitational wave astronomy was revealing, was populated with black holes in configurations and masses that existing theory had not fully anticipated. The supermassive black holes that sit at the centers of most large galaxies are objects of a different character from the stellar mass black holes formed in supernovae. The supermassive black holes range from millions to billions of times the mass of the Sun. Sagittarius. A star at 4 million solar masses is relatively modest by galactic center standards. The black hole at the center of M87, imaged in 2019, has a mass of approximately 6.5 billion solar masses. TUN 618, a quasar about 10 billion light-years away, harbours a black hole estimated at 66 billion solar masses. So massive that the event horizon would encompass a region larger than the solar system. How these objects formed is one of the major open questions of cosmological astronomy. The most straightforward mechanism would be the gradual accumulation of mass through mergers and accretion over cosmological timescales. Black holes growing by swallowing gas, dust, stars, and smaller black holes over billions of years. This mechanism certainly operates and contributes to the growth of supermassive black holes. But it faces a challenge when applied to the most distant quasars, some of which are seen at redshifts corresponding to times when the universe was less than 1 billion years old, and which already harbour black holes of 1 billion solar masses or more. Growing a black hole to that mass in that time through ordinary accretion requires either extraordinarily efficient and sustained accretion at the theoretical maximum rate, or seed black holes that were already very massive, thousands or millions of solar masses, rather than the tens of solar masses that ordinary stellar evolution produces. The origin of these massive seeds is unknown. Various mechanisms have been proposed. The direct collapse of massive gas clouds in the early universe, bypassing the ordinary stellar evolution route. The merger of the dense central star clusters that form in the earliest galaxies. The remnants of the very first generation of stars, which may have been far more massive than any stars that form today, because the early universe lacked the heavy elements that in later generations would cool the gas and prevent it from collapsing into single supermassive objects. None of these mechanisms has been definitively confirmed by observation. The relationship between supermassive black holes and the galaxies that host them is itself mysterious and apparently profound. Observations over the past 3 decades have revealed a striking correlation. The mass of the central black hole in a galaxy is tightly correlated with properties of the galaxy's bulge, the dense central region, including the velocity dispersion of the stars, the mass of the bulge, and the luminosity of the bulge. This correlation is surprising because the scale of the black hole is so much smaller than the scale of the galaxy. The event horizon of a supermassive black hole is smaller than the solar system, while the galaxy it inhabits may span thousands of light years. The black hole and the galaxy are separated by 12 orders of magnitude in size, and yet their properties are correlated. The correlation suggests a deep connection between the growth of the central black hole and the formation of the galaxy around it. That the processes that fed the black hole and the processes that built the galaxy are not independent but coupled, each influencing the other over billions of years of cosmic evolution. The specific mechanism of this coupling is called AGN feedback, where AGN stands for active galactic nucleus, the luminous phase in which the central black hole is actively accreting. When the black hole accretes rapidly, the enormous energy released, in radiation, in jets of high-energy particles, in powerful winds of gas driven outward by radiation pressure, heats and disperses the surrounding gas, suppressing star formation in the galaxy and limiting the further growth of the black hole itself. This self-regulating feedback loop, the black hole growing by accretion, the accretion generating outflows that limit the further accretion, the galaxy's star formation regulated by the black hole's activity, appears to be responsible for the tight correlation between black hole mass and galactic bulge properties. It makes the central black hole not merely a passive resident of the galaxy, but an active participant in shaping the galaxy's evolution, a kind of cosmic governor that regulates the rate at which its host galaxy forms, stars, and grows. The details of this feedback mechanism are the subject of intensive current research, because understanding how galaxies form and evolve requires understanding how their central black holes behave. The largest simulations of cosmic structure formation, the Illustris simulation, the Eagle simulation, the TNG simulations, incorporate models of AGN feedback, and the properties of the simulated galaxies agree much better with observations when AGN feedback is included than when it is not. But the specific physical processes by which the energy from the accreting black hole couples to the surrounding gas, how efficiently it heats the gas, at what scales it operates, how it depends on the properties of the black hole and the host galaxy, remain uncertain, and the different simulations use different models that give somewhat different predictions. Somewhere beyond the supermassive black holes at galactic centers, in the early and the distant universe, the most luminous objects in the observable cosmos blaze with the light of matter falling into black holes 1 billion times the mass of the Sun. Quasars, the quasi-stellar objects first identified by Martin Schmidt in the early 1960s, are the most luminous persistent sources of electromagnetic radiation in the universe. The most luminous known quasars outshine entire galaxies by factors of 1,000 or more, radiating at luminosities of tens of trillions of times the Sun's output. They are visible across almost the full observable universe. The most distant known quasar, observed in 2021, is seen at a redshift corresponding to a time when the universe was only about 670 million years old, less than 5% of its current age. The power source for this extraordinary luminosity is the accretion disk around a supermassive black hole. Gas and dust spiraling inward toward the black hole form a flattened disk structure, the accretion disk, in which the material is heated by friction and by gravitational energy as it moves to smaller orbits, radiating at temperatures of tens of millions of degrees and producing a spectrum of radiation that peaks in the X-ray and ultraviolet but extends across the full electromagnetic spectrum. The efficiency of this energy conversion, the fraction of the rest mass energy of the infalling material that is converted to radiation, is several percent compared to the fraction of a percent for nuclear fusion. The accretion disk of a black hole is, watt for watt, the most efficient energy-producing mechanism in the universe. In addition to the radiation from the accretion disk, many active galactic nuclei produce relativistic jets, narrow beams of high-energy particles and magnetic fields that emerge from the vicinity of the black hole and extend for distances of thousands or even millions of light-years beyond the galaxy, moving at velocities that are a substantial fraction of the speed of light. The jet from M87 extends for thousands of light-years and has been imaged in detail at radio, optical, and X-ray wavelengths. It is powered by the rotational energy of the spinning black hole, extracted through the interaction of the black hole's rotation with the magnetic fields threading the accretion disk, a process described by the Blandford-Znajek mechanism, which represents one of the most elegant results in relativistic astrophysics. The jets of active galactic nuclei deposit enormous amounts of energy into the intergalactic medium of galaxy clusters, the hot diffuse gas that fills the space between galaxies. And this energy deposition has profound effects on the structure of galaxy clusters and on the formation and evolution of the larger structures in the universe. The jets are, in a real sense, the fingers of the black hole reaching out into the cosmos, shaping the large-scale structure of the universe on scales that dwarf the galaxy that hosts them. At the other end of the mass spectrum from supermassive black holes lie objects whose existence is hypothetical, but whose properties have been extensively studied: primordial black holes. In the early universe, in the first second after the Big Bang, the density of the cosmos was so high that in regions where the density fluctuations happened to be somewhat larger than average, the pressure gradient might not have been sufficient to prevent gravitational collapse. In such regions, a black hole could have formed directly from the radiation-dominated plasma of the early universe, without the intermediate step of stellar evolution. These black holes, formed in the earliest moments of cosmic history, are called primordial black holes. The range of masses that primordial black holes could have spans an extraordinary range, from objects lighter than an asteroid to objects as massive as a galaxy. Their mass depends on when in the early universe they formed. A black hole forming at 1 second after the Big Bang would have a mass of approximately 100,000 solar masses, while one forming at 1 microsecond would have a mass of less than a solar mass. Primordial black holes have attracted enormous interest as a potential component of dark matter, the invisible mass that makes up approximately 27% of the universe's energy density and whose particle nature remains unidentified. If primordial black holes of a certain mass range were produced in sufficient numbers in the early universe, they could account for all or part of the dark matter without requiring any new fundamental particles. The gravitational lensing of distant stars and galaxies by such objects would be detectable, and various surveys have been conducted to look for the signature of primordial black holes acting as gravitational lenses. The results of these surveys have ruled out primordial black holes as the sole component of dark matter over large ranges of mass, but have left open some windows, particularly in the asteroid mass range, where the lensing signature is subtle and the surveys have limited sensitivity. The gravitational wave detections by LIGO have also constrained the abundance of primordial black holes in the mass range of tens of solar masses, since a large population of such objects would produce a detectable background of gravitational waves from their mergers. But the question of whether primordial black holes contribute to dark matter remains open. The formation of primordial black holes, if it occurred, would have left signatures in the cosmic microwave background, the relic radiation from the early universe, and in the distribution of large-scale structure. Current observations of the cosmic microwave background, particularly from the Planck satellite, have provided powerful constraints on the spectrum of density fluctuations in the early universe, and these constraints limit the abundance of primordial black holes but do not rule them out. Future surveys, with greater sensitivity and wider coverage, will provide tighter constraints. The behavior of matter as it approaches the event horizon of a black hole, not from the outside, as Hawking considered, but from the perspective of the matter itself and the extreme physical conditions it encounters, is one of the richest areas of black hole physics. At a large distance from a stellar mass black hole, the tidal forces, the difference in gravitational acceleration between one side of an object and the other, are small, and the approach toward the black hole can proceed without significant distortion of the infalling object. But as the distance decreases, the tidal forces grow. For an object approaching a stellar mass black hole, the tidal forces become significant when the object is still hundreds of thousands of kilometers away, and they become overwhelming as the event horizon is approached. A human being approaching a stellar mass black hole would be elongated in the radial direction and compressed in the transverse directions, a process colourfully described as spaghettification. And this elongation would continue until the structural forces holding the person together were overwhelmed by the tidal forces, at which point the person would be stretched into a long, thin stream of particles. For a supermassive black hole, the situation is different, because the tidal force at the event horizon decreases as the black hole mass increases. The event horizon is proportionally farther from the singularity for a more massive black hole. The tidal forces at the event horizon of a billion solar mass black hole are modest. An astronaut falling into such a black hole would not be spaghettified at the horizon. They would cross the horizon without immediate physical distress, experiencing nothing unusual at the moment of crossing. The horror of their situation, the fact that they could never escape, that the singularity was in their unavoidable future, would not be immediately apparent from their local experience. The equivalence principle of general relativity, the idea that freely falling observers experience the same physics as observers in empty space, would hold locally at the moment of horizon crossing. This is perhaps the most philosophically disturbing aspect of the event horizon. It is undetectable to a local observer. There is no alarm, no wall, no change in the texture of experience at the moment of crossing. The boundary between escape and no escape is invisible to the person crossing it. The prison bars are transparent. The question of what an observer actually sees inside the event horizon, what the interior of a black hole looks like, assuming the firewall conjecture is wrong and the interior is smooth, is interesting to think through. An observer who has crossed the event horizon of a Schwarzschild black hole would find themselves in a space-time region where the singularity lies in their future, not at a specific point in space. In the coordinates of the Schwarzschild interior, the singularity is everywhere in the future simultaneously. It is not a point you can avoid by moving sideways. It is the future itself. Any path the observer follows, in any spatial direction, leads to the singularity in finite proper time. The light from the universe outside the black hole would be visible to the observer. They can still receive signals from outside, though they can no longer send signals out. In the moments after crossing the horizon, the outside universe would appear concentrated in a small bright region directly above the observer, compressed by the extreme space-time curvature into a small solid angle. As the observer fell deeper, this window on the outside universe would shrink further, and the light from it would be increasingly blue-shifted. The observer would see the outside universe running forward in time, compressed into ever shorter moments from their perspective, until the singularity terminated their experience. This picture of the universe's entire future history, visible in compressed form during the fall to the singularity, is one of the strange gifts of general relativity's description of the black hole interior. Whether it is actually correct, or whether quantum effects modify it fundamentally depends on the resolution of the information paradox and the development of quantum gravity that has not yet come. The rotation of black holes, the fact that most real black holes are spinning, adds a layer of richness to their physics that is absent in the simplest Schwarzschild case. A rotating black hole is described by the Kerr metric found by the New Zealand mathematician Roy Kerr in 1963, just months after the discovery of quasars that made the understanding of rotating black holes astrophysically urgent. The Kerr solution is one of the most remarkable exact solutions to the Einstein field equations, describing a geometry that is more complex than the Schwarzschild case in ways that have profound physical consequences. The most striking feature of a rotating black hole is the ergosphere, a region outside the event horizon where space-time is dragged around so rapidly by the rotation of the black hole that it is impossible for an object to remain stationary relative to distant observers. Inside the ergosphere, all objects are dragged along in the direction of the black hole's rotation, like objects on the surface of a spinning top, regardless of what the object does with its own propulsion. The name ergosphere comes from the Greek word ergon, meaning work, because energy can in principle be extracted from this region. The mechanism for extracting energy from the ergosphere was proposed by Roger Penrose in 1969 and is called the Penrose process. In the Penrose process, an object enters the ergosphere and splits into two pieces, one of which falls into the black hole on a specific trajectory that carries negative energy, negative relative to observers at infinity. Because the total energy is conserved, the other piece escapes with more energy than the original object had, and the black hole's rotation is slightly reduced. In principle, by repeated application of the Penrose process, one could extract a substantial fraction of the rotational energy of the black hole, up to 29% of its total mass energy. The astrophysically relevant version of the Penrose process, called the Blandford-Znajek mechanism, after its discoverers, Roger Blandford and Roman Znajek, involves magnetic fields threading the ergosphere rather than infalling objects. The interaction of the rotating spacetime with the magnetic field extracts energy from the black hole's rotation and channels it into the relativistic jets that are among the most spectacular features of active galactic nuclei. The Blandford-Znajek mechanism is believed to be the primary driver of the most powerful jets in the universe. Beams of high-energy particles that can extend for millions of light years, depositing energy far from the galaxy and shaping the large-scale structure of the intergalactic medium. The maximum possible spin of a black hole, the maximum angular momentum relative to its mass, is limited by the requirement that the event horizon continue to exist. A black hole spinning faster than a certain maximum rate would have no event horizon, exposing the singularity directly to the outside universe. Such an object, called a naked singularity, is considered highly problematic. A singularity visible to outside observers would represent a complete breakdown of predictability in general relativity, since the singularity is a region where all laws of physics fail and from which, in principle, any signal or particle could emerge unpredictably. Roger Penrose proposed in 1969 the cosmic censorship conjecture, the hypothesis that nature never produces naked singularities from physically reasonable initial conditions, that whenever a singularity is about to form, an event horizon always forms around it first, hiding it from outside observers. The cosmic censorship conjecture remains unproven. It is a conjecture rather than a theorem, and there are numerical examples of initial conditions in general relativity that seem to produce naked singularities. Whether these examples represent genuine violations of cosmic censorship or artifacts of the specific initial conditions used is still debated. The resolution of cosmic censorship is connected, like so many questions in black hole physics, to the development of quantum gravity. The future of black holes, their ultimate fate over cosmic timescales, is determined by two competing processes: the accretion of matter, which adds mass, and the emission of Hawking radiation, which removes it. For any black hole in the current universe, the Hawking radiation is negligibly small, far below the temperature of the cosmic microwave background, which means the black hole absorbs more energy from the background radiation than it emits in Hawking radiation. The black holes of the current universe are growing, not shrinking, as they absorb the radiation that fills the cosmos. But the universe is expanding, and as it expands, the cosmic microwave background cools. The temperature of the background radiation decreases with the expansion of the universe, falling as the inverse of the scale factor. Eventually, in the remote future, when the universe has expanded by many orders of magnitude, the background temperature will fall below the Hawking temperature of even the most massive black holes, and the balance will tip. The black holes will begin to lose more energy through Hawking radiation than they gain from the background, and they will begin to shrink. The timescale for this evaporation is astronomical. A black hole of 1 solar mass will evaporate in approximately 10 to the 67th years, a number so large that it defies meaningful comparison with any familiar timescale. The age of the universe is approximately 14 billion years, or approximately 10 to the 10th years. The evaporation time for a solar mass black hole is 10 to the 57th times longer than the current age of the universe. A supermassive black hole of 1 billion solar masses will evaporate in a time approximately 1 billion cubed times longer still, 10 to the 96th years or so. These timescales are so vast that all ordinary astrophysical processes, the formation and death of stars, the evolution and collision of galaxies, the decay of protons if they are unstable, will have ended long before the last black holes complete their evaporation. In the very far future, the universe will consist largely of black holes and elementary particles, with the black holes slowly losing mass through Hawking radiation over incomprehensibly long timescales, growing smaller and hotter as they evaporate, until in the final moments each black hole flares briefly and brilliantly, converting its remaining mass to radiation in a burst that lasts a fraction of a second, and then is gone. The universe's final era will be defined by these brief, brilliant flares in an otherwise dark and expanding cosmos. The last black holes, the final remnants of the matter that once formed stars and galaxies and planets and living things, converting the last of their mass to light and disappearing into the expanding darkness. After that, there will be nothing but the slow cooling of the radiation. A universe growing ever colder, ever more dilute, ever more featureless, the entropy approaching its maximum value, the universe running down toward the final equilibrium state from which no further change is possible. This is the ultimate fate that the physics of black holes implies for the universe. An end state not of collapse but of dispersal, not of compression but of infinite expansion, not of darkness but of radiation cooling toward absolute zero across timescales that no language has words to properly convey. And yet, sitting with the black hole as an object, not as a fate of the universe, but as the specific, particular, extraordinary phenomenon that it is, there is something that is almost restful about its nature. A black hole is a place where the universe has been simplified to its ultimate extreme. All the complexity of the matter that formed it, the spinning electrons, the vibrating atoms, the specific arrangements of molecules that constituted whatever fell in, has been compressed in the classical picture to a singularity where no complexity remains. A black hole is described, completely and exactly, by just 3 numbers: its mass, its charge, and its spin. Everything else about it has been erased. This is the no-hair theorem. The black hole has no hair, meaning no additional features beyond these 3 numbers. And it represents a kind of perfection, a limit of simplicity that no other object in the universe achieves. The universe around us is characterized by complexity, by specificity, by the extraordinary variety of forms that matter and energy take. Stars and planets, ecosystems and civilizations, the specific arrangement of atoms that constitutes a memory, a thought, a feeling. All of this complexity exists against a background that is tending always toward simplicity, always toward higher entropy, always toward the featureless equilibrium that physics describes as the universe's ultimate destination. A black hole is, in one sense, that ultimate destination. A place where all the specific information of the matter that formed it has been swallowed, where the specificity that makes things particular has been replaced by 3 numbers. In another sense, it is the opposite, the most extreme possible departure from equilibrium, the place where the curvature of space-time is most severe, where the contrast between the organized and the simple is most stark. It is, in any case, the place where the physics of the universe reaches its most extreme expression, where the equations that describe ordinary matter and ordinary space-time reach their limits, where the next step in understanding requires ideas that have not yet been fully formed. You are lying still somewhere, drifting towards sleep, and somewhere in the universe, in your galaxy, in countless galaxies visible from Earth's sky, black holes are pulling matter into accretion disks that glow more brilliantly than any star, are emitting jets of charged particles that extend for millions of light years, are slowly evaporating through the quantum mechanical process that Hawking identified, are waiting, over timescales beyond any meaningful comprehension, to be the last structures standing in an expanding universe that has cooled to near absolute zero. And none of it, not the image, not the gravitational wave chirp, not the decades of theoretical argument, has answered the question at the center of it all. What is actually happening at the singularity, where our understanding ends? That question waits in the dark, patient as the objects it describes. To understand what might lie at the singularity, to understand what physics might replace the breakdown of classical general relativity at that extreme point, it helps to understand the scale at which the breakdown occurs and what that scale implies about the kind of theory that could describe it. The Planck scale is the name given to the regime of energies and distances at which quantum gravitational effects become equally important as quantum mechanical effects and relativistic effects. It is defined by combining the 3 fundamental constants that respectively characterize quantum mechanics, relativity and gravity: Planck's constant, the speed of light, and Newton's gravitational constant. From these 3 numbers, you can construct a length, the Planck length, of approximately 10 to the negative 35 meters. You can construct a time, the Planck time, of approximately 10 to the negative 43 seconds, and you can construct a mass, the Planck mass, of approximately 22 micrograms, roughly the mass of a flea egg. The Planck length is the scale at which the quantum fluctuations in the geometry of space-time become of order 1, at which the smooth, continuous geometry of classical general relativity is replaced by something else, something that our current theories cannot describe. It is approximately 10 to the negative 20 power times smaller than the proton, itself already 10 to the negative 15 meters across. The ratio of the Planck length to the size of an atom is roughly the same as the ratio of an atom to the observable universe, an almost incomprehensible difference in scale that illustrates why quantum gravitational effects are negligible in all experiments we can currently conduct, and why the incompatibility between quantum mechanics and general relativity is a theoretical rather than an immediately observational problem. The Planck density, the density at which quantum gravitational effects become important, is approximately 10 to the 96 kilograms per cubic meter. For comparison, the density at the center of a neutron star, The densest conventional astrophysical object is approximately 10 to the 18th kilograms per cubic meter. The density at which quantum gravity becomes important is roughly 10 to the 78 times denser than the densest neutron star. This is the density that would be reached at the classical singularity of a black hole, and it is the density that a complete theory of quantum gravity must be able to describe. What might physics look like at the Planck scale? The honest answer is that nobody knows, because no theory of quantum gravity has been fully developed and confirmed. But there are hints, constraints, and partial results from the leading candidate frameworks that suggest certain features of what a complete theory might look like, and these features are strange enough to be worth dwelling on. String theory, as described in the context of its derivation of black hole entropy, replaces the point particles of the Standard Model with one-dimensional strings. The characteristic size of a string, the string length, is near but not necessarily identical to the Planck length, and in some formulations it is somewhat larger, with the Planck length arising as a derived scale from the interplay between the string length and the string coupling constant. The fundamental entities of string theory are not point-like but extended, and their extended character resolves the ultraviolet divergences, the infinities that plague quantum field theories when interactions occur at arbitrarily small scales, that have prevented a consistent quantum theory of gravity based on point particles. In the string theory picture of what happens at a black hole singularity, the infinite density predicted by classical general relativity is expected to be replaced by a regime of extremely high but finite string density, where the physics is described by the interactions of highly excited strings rather than by classical geometry. The strings can be in highly excited states, winding around the compactified extra dimensions, vibrating at high frequencies, carrying large amounts of energy in their oscillation modes, and these excited states provide the microscopic degrees of freedom that Bekenstein postulated must underlie black hole entropy. The specific picture of the black hole singularity in string theory is not fully worked out, partly because the calculations become intractable in the strongly curved geometries near the singularity, where the approximations that make string theory calculable break down. But the general expectation is that the singularity is resolved, that the infinities of classical general relativity are replaced by finite values when the full string theory physics is taken into account, and that the resolution involves the excitation of stringy degrees of freedom that have no analogue in the classical or field theoretic descriptions. The extra dimensions that string theory requires are themselves connected to the resolution of singularities in a subtle way. The specific geometry of the compactified extra dimensions can undergo transitions, changes in topology, changes in the shape of the extra dimensions that, in the classical picture, would involve the appearance of singularities. String theory handles these transitions smoothly, with the singularity that would appear in the classical description being replaced by a region where the extra dimensions undergo a topological change that is physically sensible in the string description but geometrically singular in the classical one. This resolution of classical singularities by string effects is one of the most striking demonstrations that string theory represents a genuinely new description of space-time rather than a mere modification of existing theories. The 11-dimensional theory that unifies the 5 consistent string theories, called M-theory, where M has been interpreted as standing for membrane, matrix, magic, mystery, or mother, depending on who is being asked, extends the string description by including 2-dimensional objects called membranes or branes and higher dimensional generalizations. The M-theory landscape, with its 10 dimensions of space and 1 of time, includes the various compactifications that give rise to the different string theories as limiting cases, and is widely believed to be the fundamental framework of which string theories are approximations. But M-theory has not been fully formulated. Its precise equations are not known, only its low energy limit in various approximations, and its implications for black hole singularities are correspondingly uncertain. The loop quantum gravity approach to the singularity, as briefly described earlier, predicts that the classical singularity is replaced by a quantum bounce at the Planck density. The specific mechanism involves the discrete quantum geometry of loop quantum gravity, which prevents the compression of matter to arbitrarily small volumes. When the volume of a region reaches the Planck volume, the smallest volume that has physical meaning in the loop quantum gravity framework, the quantum pressure of the discrete geometry resists further compression, just as the Pauli exclusion principle prevents electrons from being compressed into arbitrarily small volumes in ordinary quantum mechanics. The cosmological application of this same idea, loop quantum cosmology, has been used to study the behavior of the universe at the very beginning, when the Big Bang singularity of classical cosmology would occur. In loop quantum cosmology, the Big Bang singularity is replaced by a big bounce. The universe contracts to a maximum density at the Planck scale, then bounces and begins expanding again. The pre-bounce universe, the universe before the Big Bang, was a contracting universe, and the Big Bang was the moment of minimum volume rather than a creation from nothing. This picture, if correct, has profound implications for cosmology. It implies that time extends before the Big Bang, that the universe has a history stretching back before the moment that classical cosmology treats as the beginning, and that the specific properties of our current universe, the pattern of density fluctuations, the spectrum of primordial gravitational waves, the ratio of matter to radiation, are determined not only by the physics of the immediately post-Big Bang era, but by the physics of the contracting pre-bounce phase. The specific predictions of loop quantum cosmology for observable quantities, the power spectrum of the cosmic microwave background, the level of primordial gravitational waves, are being calculated with increasing precision and will be tested by future experiments including the LightBird satellite and the Simons Observatory. Whether loop quantum cosmology's predictions agree with observation will provide a significant test of the framework and therefore an indirect test of the loop quantum gravity approach to the black hole singularity. The connection between the cosmological bounce and the black hole bounce, the same physics of quantum geometry resolution applied to the cosmological singularity and to the black hole singularity, suggests a picture in which the universe is populated not only by black holes that contain new expanding regions, but by those new regions themselves containing black holes that give rise to further new regions in an infinite recursive structure of universes within black holes within universes. This picture has been explored by Lee Smolin under the name cosmological natural selection. The idea that the parameters of the physical laws are determined by a selection process analogous to natural selection, in which universes that produce many black holes produce many offspring universes, and the parameters evolve toward values that maximize black hole production. The idea is intriguing, but has not been sufficiently constrained by observation to be regarded as established. The tension between the different candidate theories of quantum gravity, string theory, and loop quantum gravity being the most developed, is not merely a technical dispute about calculational methods. It reflects a deeper disagreement about what the fundamental entities of nature are and what the relationship between quantum mechanics and space-time geometry should be. String theory takes a particle physics perspective. It starts with matter and forces, described by quantum mechanics, and it modifies the description by replacing point particles with strings and embedding the whole structure in extra dimensions. The geometry of space-time arises from the vibration modes of strings and from the structure of the extra dimensions, but the quantum mechanical framework, the Hilbert space, the evolution equation, the probabilistic interpretation is taken for granted from the outset. Loop quantum gravity takes a general relativistic perspective. It starts with the insight that space-time geometry is dynamical, that it evolves and responds to matter, and it applies the quantization procedure to space-time geometry itself, treating the connections and loops that describe the geometry as quantum operators. The result is a quantum theory in which the geometry of space is discrete and quantized at the Planck scale, but the matter fields and their quantum mechanical description are secondary to the geometry. The two approaches give different answers to the question of what space and time are at the fundamental level. For string theory, the extra dimensions and the string landscape suggest that space-time is not a fixed four-dimensional structure, but can exist in many different configurations, each corresponding to a different compactification of the extra dimensions. The specific four-dimensional space-time we observe is one configuration among a vast landscape of possibilities, and the question of why we are in this configuration rather than another is connected to the landscape problem and the anthropic principle. For loop quantum gravity, the four-dimensional structure of space-time is not an accident of compactification, but a fundamental feature of the theory. The quantum geometry is four-dimensional from the outset, built from the loops and networks that define the discrete structure of space. The extra dimensions of string theory play no role, and the landscape problem does not arise in the same way. Whether these two frameworks are ultimately compatible, whether they are approximations to the same underlying theory, or whether they represent genuinely different physical pictures, is not known. Some researchers have speculated that M-theory and loop quantum gravity might both be aspects of the same more fundamental structure, but the technical differences between them have made explicit comparison difficult. The development of quantum gravity is still at a stage where multiple frameworks compete without any definitive empirical criterion to distinguish between them. The most direct observational test of quantum gravity effects near black holes would be the detection of the final burst of radiation from the evaporation of a primordial black hole. As discussed earlier, primordial black holes of sufficiently small mass, specifically those with an initial mass less than approximately 10 to the 12 kilograms, roughly the mass of a large asteroid, would have evaporated by now, with the final burst occurring in the current epoch of the universe. If such black holes were formed in the early universe, and if some of them are evaporating now, the final burst would be detectable as a brief flash of high-energy gamma rays and other particles from the direction of the evaporating black hole. The specific spectrum of the final burst, the distribution of particle energies in the last moments of evaporation, would depend on the physics of quantum gravity at the Planck scale. In the standard Hawking calculation, the burst spectrum is thermal, with a temperature that rises as the black hole loses mass, becoming a brief flare of extreme intensity as the mass approaches zero. But if quantum gravity modifies the Hawking radiation in the final stages, if the discrete quantum geometry of loop quantum gravity or the string description affects the radiation when the black hole reaches Planck scale dimensions, the spectrum would deviate from the thermal prediction. Detection of this deviation would be a direct test of quantum gravity theory. The challenge is that no evaporating primordial black hole has yet been detected, despite searches by gamma-ray telescopes, including the Fermi Gamma Ray Space Telescope. The absence of detection constrains the abundance of primordial black holes in the relevant mass range, ruling out scenarios in which they are so common that their bursts would have been detected already. But it does not rule out the possibility that they exist at lower abundance, and future searches with more sensitive instruments might detect the first evaporating primordial black hole. An event that would be not only the first direct observation of Hawking radiation, but a window into the Planck scale physics that no other observation can access. The role of black holes in the origin of life is not obvious, but it is real, if indirect. The heavy elements that are essential for life, carbon, nitrogen, oxygen, phosphorus, iron, and many others, were produced in stellar nucleosynthesis and distributed through the galaxy by stellar explosions. the most massive stars, which produce the heaviest elements and which end their lives in the supernovae that form stellar mass black holes, are therefore responsible both for the creation of black holes and for the production of the material from which planets and living things are made. More directly, the X-ray radiation from accreting black holes in binary star systems has been proposed as a potential energy source for prebiotic chemistry, for the chemical reactions that produce the first complex organic molecules on the early Earth. The relationship between black hole X-ray emission and the radiation environment of early Earth is not established, but it illustrates the way in which the physics of extreme objects can have consequences that reach all the way down to the chemistry of life. The timing of life's appearance on Earth is also connected in an indirect way to the black hole at the center of our galaxy. Sagittarius, a star which is currently quiescent, was apparently much more active in the past. Several tens of millions of years ago, there is evidence from gamma-ray observations by the Fermi telescope of a massive outburst from the galactic center, producing a pair of enormous structures called the Fermi bubbles that extend thousands of light years above and below the galactic plane and are still expanding outward. If Sagittarius A star was more active earlier in the galaxy's history, the radiation environment at the location of the solar system may have been significantly different, and this may have influenced the conditions for life's emergence and early evolution. The connections between the physics of black holes and the biology of life are tenuous and speculative at this level, but they illustrate a general principle. The universe is not a collection of independent phenomena, each isolated from the others, but an interconnected system in which the physics of extreme objects influences the conditions for chemistry and biology across vast scales of time and space. In the winter of 2015, a small team of physicists and engineers in the control room of the LIGO detector in Hanford, Washington, were watching the output of their instrument on a Monday morning when they noticed something. The data channels were showing a pattern, a brief oscillation rising in frequency over a fraction of a second that looked unlike any terrestrial noise source they had catalogued. The signal appeared in both Hanford and in Livingston, Louisiana, with a time delay of 7 milliseconds, consistent with the propagation of a signal at the speed of light between the two sites. The team had been expecting something like this. The LIGO detectors had been upgraded over the previous several years from their initial configuration, Advanced LIGO, with new mirrors, new laser systems, new seismic isolation systems that had increased their sensitivity by a factor of 3. The upgrade had been completed only 2 days before the detection. The timing was either extraordinarily fortunate or simply the consequence of the fact that at the new sensitivity level, merging black holes at the relevant distances were expected to be detected roughly once every few weeks. The signal, designated GW 150914 for its detection date of September 14, 2015, was consistent with the gravitational waves produced by the merger of two black holes at a distance of approximately 1.3 billion light-years. The masses of the merging objects were approximately 36 and 29 times the mass of the Sun, and the final merged object had a mass of approximately 62 solar masses. The missing 3 solar masses had been radiated away as gravitational waves in the brief moment of the merger. The detection was not announced immediately. The LIGO team spent 5 months verifying the result, checking every possible source of terrestrial or instrumental noise that might have produced a similar signal, confirming that the signal's properties, its duration, its frequency evolution, its amplitude, matched the predictions of general relativity for a black hole merger rather than any known noise source. They brought in external reviewers. They wrote the paper. They argued about the analysis. They were as confident as scientists can be before they went public. The announcement, made on February 11, 2016, at a press conference in Washington, D.C., that was simultaneously broadcast to institutions around the world, was received with the kind of excitement that is rare in the culture of science. Hundreds of scientists gathered in auditoriums to watch the press conference live. Physicists who had worked for decades on the development of gravitational wave detectors, whose careers had been sustained by the expectation of detection, but who had not yet seen it, heard the announcement and wept. The quality of the emotion in the room, a mixture of scientific exhilaration and personal relief after long effort, was visible even through the video feeds. The Nobel Committee moved with unusual speed. The Nobel Prize in Physics for 2017 went to Rainer Weiss, Kip Thorne, and Barry Barish, the physicists most responsible for the conception, development, and leadership of the LIGO project. The prize cited the detection of gravitational waves and the direct observation of merging black holes. The committee did not have to wait long. The discovery was sufficiently important that awarding it within 2 years of the detection was considered appropriate. Since that first detection, the catalogue of gravitational wave events has grown steadily. The second observing run of advanced LIGO added several more black hole mergers. The third observing run, conducted jointly with the Virgo detector in Italy, added dozens more, including the first detection of a neutron star merger, an event designated GW 170817, which was observed simultaneously in gravitational waves by LIGO and Virgo, and in electromagnetic radiation across the full spectrum from gamma rays to radio, providing a spectacular demonstration of multi-messenger astronomy and enabling the most precise test of the equivalence of the speed of light and the speed of gravity ever conducted. The neutron star merger was also the source of the first direct production of heavy elements, gold, platinum, and other elements heavier than iron, confirmed in real time by the spectroscopic observation of the optical counterpart. The neutron star merger that produces gravitational waves also produces the R-process nucleosynthesis that creates the heaviest elements in the periodic table. And the observation of GW 170817 confirmed what theorists had long suspected, that much of the gold in the universe, including the gold in any jewelry you might be wearing, was produced in the violent collision of two neutron stars billions of years ago and distributed through the galaxy to eventually become part of the planet on which you were formed. The most recent generation of gravitational wave detectors, LIGO, at improved sensitivity, Virgo, and the new Kagra detector in Japan, are now observing multiple events per week during their observing runs, and the catalogue of black hole mergers has grown to dozens of confirmed events with dozens more candidates. The next generation of detectors, the Einstein Telescope in Europe and Cosmic Explorer in the United States, will be an order of magnitude more sensitive, capable of detecting black hole mergers anywhere in the observable universe and reconstructing the population of black holes with statistical precision. The space-based gravitational wave detector LISA, planned for launch in the 2030s, will detect a different class of sources: the slow, low-frequency gravitational waves produced by the inspiral of stellar mass compact objects into supermassive black holes. Extreme mass ratio inspirals, or EMRs, and by the mergers of supermassive black holes following the collision of their host galaxies. EMRs will allow the mapping of the space-time geometry near supermassive black holes with extraordinary precision, testing general relativity in the strong field regime that ground-based detectors cannot access. Supermassive black hole mergers, if they occur at the rate suggested by the observed rate of galaxy mergers, should be detectable by LISA throughout the observable universe, providing a history of the assembly of supermassive black holes from the earliest cosmic times to the present. The Event Horizon Telescope, the global network of radio telescopes that produced the first image of a black hole in 2019, is itself being upgraded and expanded, with new telescopes being added to the network and existing telescopes being equipped with improved receivers to produce higher resolution images with better sensitivity. Future images of M87 and Sagittarius A star will show more detail in the ring of light around the black hole's shadow, including the possibility of resolving the photon ring, the sequence of nested images produced by photons that have orbited the black hole multiple times before escaping, which is a specific prediction of general relativity that would test the theory in a new regime. The photon ring is particularly interesting because its properties, its diameter, its brightness, and the spacing between successive images depend only on the mass of the black hole and the predictions of general relativity, independent of the properties of the accreting matter that produces the light. Measuring the photon ring would therefore provide a clean test of general relativity in the strong field regime, uncontaminated by the uncertainties in the modeling of the accretion process. Current Event Horizon Telescope images do not have the angular resolution to resolve the photon ring directly, but the next generation of the instrument, with the addition of space-based antennas that would increase the effective baseline beyond the diameter of the Earth, would potentially achieve this. The space-based extension of the Event Horizon Telescope, under study as the Event Horizon Explorer concept, would place radio antennas in orbits ranging from low Earth orbit to orbits at the Earth-Moon distance, creating a virtual telescope with a baseline hundreds of times larger than the Earth's diameter and a corresponding increase in angular resolution. With such an instrument, it would be possible not only to resolve the photon ring of Achille M87 and Sagittarius A star, but to image structures at the scale of the event horizon itself, the very boundary from which nothing escapes, in the sense of observing the shadow cast by the event horizon against the bright background of the accretion disk with sufficient resolution to see individual features. The imaging of a black hole event horizon at the level of resolution that the Event Horizon Explorer would achieve is not merely a technological achievement. It is a scientific program. It would allow tests of general relativity in conditions more extreme than any current test, measurement of the black hole's spin and mass with unprecedented precision, and possibly the detection of deviations from the Kerr geometry that would signal new physics, new theories of gravity, new matter fields, or quantum gravitational effects near the horizon. Among the most productive recent developments in the intersection of black hole physics and quantum information theory is the study of quantum chaos and its relationship to the scrambling of information in black holes. The concept of quantum chaos is subtle because the linear nature of quantum mechanical evolution, the fact that the Schrödinger equation is linear, would seem to preclude the sensitive dependence on initial conditions that characterizes classical chaos. In quantum mechanics, nearby states do not diverge exponentially in the way that classical chaotic trajectories do, but there is a quantum analog of chaos associated with the rapid spreading of quantum information through the system. The fast scrambling that we discussed in the context of Hayden and Preskill's work on black holes. A specific measure of this quantum chaos, the out-of-time order correlator, or OTOC, has been found to decay exponentially at a rate called the Lyapunov exponent, in analogy with classical chaos. For a black hole described by the ADS/CFT correspondence, the Lyapunov exponent is exactly 2p times the Hawking temperature, a result that follows from the properties of the near-horizon geometry in general relativity. This is, in essence, a derivation of the quantum chaos of a black hole from its gravitational properties. What makes this result deeply interesting is a subsequent conjecture by Juan Maldacena, Stephen Schenker, and Douglas Stanford, that the Lyapunov exponent of any quantum system with a large number of degrees of freedom is bounded above by 2 pi times the temperature, with the bounds saturated by black holes and by certain exactly solvable quantum mechanical models called Sachdev-Yekitaev models. The bound on quantum chaos, if it is indeed universal, would mean that black holes are the fastest information scramblers in nature, and that any physical system that approaches this scrambling rate is in some sense behaving like a black hole. The Sachdev-Yekitaev model, which was constructed to study non-Fermi liquids in condensed matter physics before its connection to black holes was recognized, is a simple quantum mechanical model of a large number of fermions with random all-to-all interactions. Its simplicity makes it exactly solvable, and the solution reveals a low-energy behavior that is equivalent through the ADS/CFT correspondence to a two-dimensional gravity theory in ADS space. The SYK model is thus a toy model of holography, a simple quantum mechanical system that is equivalent to a gravitational theory, and it provides a laboratory for studying the properties of black holes in a computationally tractable setting. The discovery of the SYK model's connection to black hole physics sparked an enormous body of research at the intersection of condensed matter physics, quantum information theory, and quantum gravity. Researchers have studied how the scrambling properties of the SYK model relate to those of real black holes, have used the model to study the geometry of the black hole interior, and have explored how the model might be realized in laboratory systems, potentially including systems of cold atoms or quantum dots, that would allow aspects of black hole physics to be studied experimentally for the first time. The prospect of studying black hole physics in a laboratory is extraordinary. The physics of information scrambling near the horizon, the analogue of Hawking radiation in a quantum system, the quantum chaos that connects the SYK model to gravitational physics, all of these could, in principle, be probed in experiments on quantum systems that are small enough to fit on a benchtop, but whose mathematical description is equivalent to the physics of a black hole. This does not mean that the benchtop experiment involves a real black hole or even a real analogue of gravity. It means that the mathematical structure of the quantum system is the same as the mathematical structure that describes the black hole, and that measuring certain properties of the quantum system would therefore give information about the properties of the black hole that could not be measured directly. This approach, using mathematical equivalences to study physically inaccessible systems through laboratory analogues, is not unique to black hole physics. Analog gravity experiments have attempted to create sonic analogues of the event horizon, where the flow of a fluid becomes supersonic and sound waves cannot propagate back upstream, just as light cannot propagate back out of a black hole. In these sonic black holes, the analogue of Hawking radiation, the spontaneous emission of sound at the horizon due to quantum vacuum fluctuations, has been reported in experiments using Bose-Einstein condensates. These experiments do not probe the same physics as a real black hole. The quantum field theory in a BEC is not the same as quantum field theory in curved space-time, but they test the mathematical framework of Hawking's calculation in a controlled laboratory setting and provide confidence that the underlying physics is correct. The question of what it would be like to fall into a black hole, not the tidal distortion and spaghettification of the stellar mass case, but the smooth crossing of the horizon of a supermassive black hole, is one that human beings cannot answer from direct experience, but which physics can address in some detail. For an observer falling freely toward the event horizon of a supermassive black hole like M87's, the approach would be unremarkable for a long time. The black hole would not be visible as a dark object in space. There would be no light from it to define its shape. What would be visible would be the accretion disk, a bright glowing ring of gas heated to millions of degrees, distorted by the gravitational lensing into a complex pattern of images in which the disk appears both above and below the black hole, its near side brightened by Doppler boosting, and its far side visible as a ring of light bent around the back. As the observer fell closer, the accretion disk would expand in angular size. The gravitational lensing would become more dramatic, with multiple images of distant objects appearing, light that had orbited the black hole 1, 2, 3 times before reaching the observer's eyes, creating nested rings of images. The sky would begin to appear strange, with the distribution of stars and galaxies distorted by the gravitational bending of light, concentrated toward the direction behind the observer as the black hole's gravity captured light from a wider and wider cone. At the event horizon itself, at the moment of crossing, the observer would not notice anything locally unusual. No alarm, no wall, no change in the laws of physics as they experience them locally. The equivalence principle holds. A freely falling observer is locally indistinguishable from an observer in empty space. The horizon is a feature of the global causal structure of space-time, a statement about which events can send signals to which other events, and not a local physical boundary. But in the moments after crossing the horizon, the observer's view of the outside universe would change. The light from outside the black hole, from stars, from the accretion disk, from the cosmic microwave background, would be visible, concentrated in a bright spot in the direction of the horizon directly overhead. This spot would shrink as the observer fell deeper, and the light would become progressively blue-shifted to shorter wavelengths, higher energies, as the photons from outside fell deeper into the gravitational well to reach the observer. The time remaining before the singularity, the maximum proper time that can elapse between horizon crossing and reaching the singularity, is finite and depends on the mass of the black hole. For M87's black hole, the proper time from horizon crossing to the singularity in the classical Schwarzschild description is approximately 30 hours. For Sagittarius A star, it would be approximately 20 seconds. During this time, the observer would see the outside universe, but in compressed, rapidly accelerating form, as the blue-shifted photons brought information about successively later moments in the external universe's history. What happens at the singularity? What the observer experiences in the final moments before the classical geometry breaks down is not described by any current theory. Whether the singularity is truly a place of infinite density and infinite curvature, or whether quantum gravity replaces it with something finite, is the open question that this entire journey has been moving toward. The honest answer remains, we do not know. The study of black holes has changed the culture of theoretical physics in ways that go beyond the specific results it has produced. It has brought together communities of researchers who previously had little contact, particle physicists and general relativists, condensed matter physicists and string theorists, quantum information theorists and astrophysicists, and created a shared set of problems around which these communities have organized. The information paradox, the firewall controversy, the holographic principle, the quantum chaos of black holes. These are problems that require expertise from multiple domains, and their study has driven a cross-fertilization of ideas that has been unusually productive. The holographic principle itself, the idea that the information content of a region of space is encoded on its boundary, originated in black hole physics and has become one of the organizing principles of the entire field of quantum gravity. The ADS/CFT correspondence that realizes the holographic principle precisely has been applied not only to questions about black holes, but to questions about the strong nuclear force, about heavy ion collisions, about the behavior of condensed matter systems near phase transitions, about the properties of superconductors. The mathematical machinery of string theory and quantum field theory in curved space-time, developed to address the questions raised by black holes, has found applications in areas of physics that have no obvious connection to gravity. This is not unusual in the history of physics. The development of statistical mechanics to understand thermodynamics led to the kinetic theory of gases and eventually to the atomic theory of matter. The development of quantum mechanics to understand the spectrum of the hydrogen atom led to the understanding of chemical bonding and eventually to the entire edifice of modern chemistry and materials science. The development of general relativity to understand gravity led to cosmology and eventually to the understanding of the large-scale structure and evolution of the universe. The specific problem generates the tools, and the tools are found to apply far beyond the specific problem that generated them. The tools that black hole physics has generated, the techniques of quantum field theory in curved space-time, the mathematical framework of ADS/CFT, the concepts of holography and entanglement entropy and quantum chaos are already being applied far beyond their origins, and the full scope of their applications is not yet apparent. What the physics of the most extreme objects in the universe will eventually teach us about the nature of matter, information, space, and time is something that will only become clear as the field continues to develop. The first human beings who studied the night skies systematically, who noted the positions of stars, tracked the motions of planets, recognized the patterns of the seasons in the distribution of the heavens, did so without any understanding of what the objects they were observing actually were. The stars were lights fixed to a celestial sphere, or flames burning on the vault of the sky, or the eyes of gods or animals traced in the patterns of the constellations. The sun was a chariot driven across the sky, or a disk swallowed by a goddess each evening and reborn each morning, or a ball of fire fed by the vapor of the ocean. The universe they inhabited was small, human-scaled, bounded, alive with intentional forces that could be appeased or angered. In the centuries since the scientific revolution, the universe has been revealed to be incomparably larger, older, stranger, and more impersonal than anything those early observers imagined. The stars are not lights on a sphere, but suns at enormous distances, each a fusion reactor sustaining itself against gravitational collapse, each eventually exhausting its fuel, and dying in processes that range from the quiet dimming of a white dwarf to the catastrophic explosion of a supernova that seeds the galaxy with the elements of life. The galaxies are collections of hundreds of billions of such stars, held together by gravity and shaped by the evolution of the black holes at their centers. The universe itself is expanding from a hot, dense state 13.8 billion years ago. It's a large-scale structure shaped by the quantum fluctuations of an inflationary epoch that occurred in the first moments of its existence. And at the center of most galaxies, including our own, sits the object whose nature was anticipated by an English clergyman in 1783, theorized by Einstein's general relativity in 1916, described in its essential physics by Oppenheimer and Snyder in 1939, named by John Wheeler in 1967, found to radiate thermally by Hawking in 1974, imaged for the first time in 2019, and detected through its gravitational wave emissions since 2015. A region of space-time from which light cannot escape, surrounded by a horizon that is invisible to local observers, containing at its center a place where our understanding ends. The arc from John Michel's calculation at the end of the 18th century to the first image of a black hole shadow at the beginning of the 21st century is, in some ways, the arc of modern physics. From the initial mathematical prediction, through the theoretical development, through the observational confirmation, to the frontier of understanding where the confirmed phenomena raise questions that the confirming theory cannot answer. It is the arc of a science that takes its own predictions seriously enough to follow them wherever they lead, even when they lead to places as strange as the interior of a black hole, or as counterintuitive as the holographic encoding of three-dimensional space on a two-dimensional surface. The night around you, right now, is filled with the remnants of that same light that Einstein's equations predicted would be affected by gravity, bent around massive objects, shifted in frequency, slowed in its passage through gravitational wells. The specific configuration of photons entering your closed eyelids right now, and the specific configuration of gravitational waves passing through your body right now, are shaped by the black holes and neutron stars and massive galaxies between you and the sources of those photons and waves. The universe has left its imprint on the light that surrounds you in the specific, testable, quantifiable way that general relativity predicts. The physics that describes this, that derives the bending of light from the curvature of space-time and the curvature of space-time from the distribution of mass and energy, is the same physics that describes the event horizon, the singularity, the Hawking radiation, the information paradox. It is a single framework, internally consistent, extraordinarily well tested in the regimes where tests are possible, and pointing beyond itself toward the quantum gravity that will be needed to describe the regimes where tests are not yet possible. You are lying still in the dark, and in the center of your galaxy, Sagittarius. A star is quiet tonight by the standards of active galactic nuclei. 4 million solar masses compressed into a region smaller than the solar system, its accretion rate low, its luminosity faint, its event horizon invisible even to the most sensitive telescopes on Earth. 27,000 light-years away, across the spiral arms of the Milky Way, across the dust and gas and the billions of stars that intervene, the black hole sits at the gravitational center of the galaxy, shaping the orbits of the stars nearest to it, bending the space-time of the galactic core, and carrying within its interior the unresolved question that the best theoretical physics of the past century has not yet answered. What is happening there, right now, at the singularity? What is the physics that replaces the breakdown of classical general relativity at the center of the black hole? What happens to the information that falls past the event horizon, the information that has been falling into Sagittarius, a star, for billions of years? The information of gas clouds and dust and stars and perhaps other things that have approached too close. Where does that information go and does it return? These questions are not answered. They wait. They wait with the specific patience of problems that are genuinely hard, not problems that have been overlooked or that require only more computation, but problems that are hard because they require ideas that have not yet been formed. The resolution of the information paradox, the description of the singularity by quantum gravity, the understanding of how space-time emerges from more fundamental degrees of freedom, these are problems that will require physicists of the next generation to think differently about the nature of reality than any generation has thought before. That is perhaps the most remarkable thing about black holes. Not that they are extreme, though they are. Not that they are common, though there are 40 million of them in our galaxy alone. Not that they are beautiful, in the specific way that mathematical structures of extraordinary elegance are beautiful, though they are that too. The most remarkable thing is that the study of these objects, these collapsed remnants of dead stars, these power sources for the brightest objects in the universe, these endpoints of matter's long journey from hydrogen to everything and back, has revealed that we do not understand the most fundamental things about the nature of physical reality. Space may be emergent, time may be emergent. The three-dimensional world we experience may be the holographic projection of information encoded on a boundary. Quantum mechanics and gravity may be aspects of a single unified framework that is not yet known. The information that falls into a black hole may return, encoded in the Hawking radiation in a way that no current calculation can extract. All of this may be true, and the evidence, indirect, mathematical, suggestive, increasingly compelling, points in these directions. The universe is stranger than the universe we thought we understood. It is stranger, and it is richer. And the strangeness is not a deficiency of our understanding, but an invitation to understanding that has not yet been achieved. You are at the edge of sleep, in a universe full of black holes, in a galaxy whose center harbors one of them, on a planet whose atoms were made in stellar interiors and distributed by stellar explosions and assembled by chemistry into the particular configuration that is experiencing this moment. The black holes shape the galaxy that made the stars, that made the atoms that made you. The same physics that describes the event horizon describes the fate of the light that curved around massive objects on its long journey to your eyes. You are not separate from the physics of extreme objects. You are a consequence of it. The singularity waits in the dark. Physics reaches toward it with every tool at its disposal. And in the reaching, in the pursuit of what lies at the boundary of the known, in the construction of ideas subtle enough to describe what happens when space-time itself collapses. In all of this, something is happening that is not so different from what happens when a mind, approaching sleep, lets go of the familiar shapes of the waking world and drifts toward the unknown territory of the night. Both journeys end in darkness. Both begin again. And yet, before sleep fully arrives, there is more to say. The universe does not close its account with a single paragraph, and the story of black holes is not exhausted by what has been described. There are lives that shaped this science, experiments that changed what we thought we knew, and a future of discovery that is already beginning to take its first steps. The quiet around you is full of it, full of the ongoing work, the unresolved tensions, the extraordinary patience of a science that measures its timescales in decades and its distances in billions of light years. The life of Vera Rubin deserves more than the passing mention it has received so far, because her story is not only the story of dark matter, the invisible substance that makes the rotation curves of galaxies flat and whose nature remains one of the deepest mysteries in astrophysics, but the story of doing science in a context that actively worked against her and doing it with a quiet persistence that ultimately changed the field. Rubin was born in Philadelphia in 1928, the daughter of a telephone company engineer. Her father built a crude telescope for her from cardboard and other materials when she was 10 years old, and she spent nights at her bedroom window tracking the motion of the stars, filling notebooks with the records of her observations. She went to Vassar, one of the few universities at the time that admitted women to its astronomy program, and wanted to go to Princeton for graduate school. Princeton did not admit women to its graduate program in astronomy until 1975. She went to Cornell instead, then to Georgetown, completing her PhD in 1954. Her doctoral thesis proposed that galaxies were not distributed uniformly throughout the universe, but clustered into larger structures, a prediction that was ahead of its time and was initially met with skepticism, but was eventually confirmed when large-scale structure surveys made it possible to map the distribution of galaxies across hundreds of millions of light years. She was right, and the field acknowledged it only years later. At Georgetown, and then at the Carnegie Institution of Washington, Rubin began the systematic work on galaxy rotation curves that would become her most important contribution. She was not the first to notice the anomaly. Fritz Zwicky had pointed to the mass discrepancy in galaxy clusters in the 1930s, and various researchers had made measurements of individual galaxies that suggested something unusual. But Rubin, working with her collaborator, Kent Ford, and his highly sensitive spectrograph, produced the first comprehensive, systematic measurements of rotation curves for a large sample of galaxies, galaxy after galaxy, showing the same flat profile that could not be explained by the visible matter. The resistance to the interpretation of these results as evidence for dark matter was significant. Rubin presented her findings with scrupulous care, always noting the alternatives, always acknowledging the uncertainty. She did not argue for dark matter as a dramatic discovery, but as an unavoidable conclusion from careful measurement. She gave others the credit for the earlier observations, the earlier theoretical suggestions, the earlier hints of the same phenomenon, and she continued measuring galaxy after galaxy for decades, building the evidential base that made it impossible to dismiss the result as an artifact of special conditions or limited data. She was nominated for the Nobel Prize in Physics multiple times and never received it. Many of her colleagues considered this a serious failure on the part of the Nobel Committee. The evidence for dark matter from rotation curves was as compelling as many other observations that had been recognized with the prize, and her role in establishing that evidence was undeniable. She died in 2015, and the question of dark matter, the question she spent her career making impossible to ignore, remains open. The identity of dark matter is connected to the physics of black holes in several ways. If dark matter is made of weakly interacting massive particles, as the most popular model suggested for several decades, then dark matter particles should occasionally annihilate when they encounter their antiparticles, typically their own particles, since most WIMPs are their own antiparticles, producing high-energy gamma rays that could be detected. The region near the supermassive black hole at the center of the galaxy, where dark matter density is expected to be highest, would be the most productive region to look for this signal. Various gamma-ray telescopes, including the Fermi Gamma Ray Space Telescope, have searched for excess gamma-ray emission from the galactic center that could be attributed to dark matter annihilation. The results have been ambiguous. There is an excess of gamma rays from the galactic center compared to simple background models, but whether this excess is due to dark matter or to unresolved point sources such as millisecond pulsars is still debated. The connection between dark matter and black holes is most direct in the primordial black hole dark matter scenario discussed earlier. But even if primordial black holes do not constitute all of dark matter, they could still coexist with particle dark matter in some proportion, contributing to the observed gravitational effects, while the remainder is accounted for by undiscovered particles. The constraints on primordial black holes from gravitational lensing, from the cosmic microwave background, and from gravitational wave observations, when combined, leave open only certain mass windows where they could be a significant component of dark matter, and future surveys will progressively close or confirm those windows. The specific problem of the galactic center, the region within a few light-years of Sagittarius A star, has become one of the most productive testbeds for the physics of black holes in the current era. The density of stars near the galactic center is extraordinary. Within the innermost parsec, the stellar density is 10 million times higher than in the solar neighborhood, and the stars orbit the central black hole at speeds of thousands of kilometers per second. The infrared astronomers who study these stars, the groups led by Andrea Ghez at UCLA and Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics in Garching, have spent 3 decades tracking the orbits of hundreds of stars in the galactic center region, using adaptive optics systems that compensate for the blurring of the Earth's atmosphere to achieve angular resolutions comparable to those of space telescopes. The result is the most precise determination of the mass and position of Sagittarius A star that currently exists, and the most detailed tests of general relativity in the vicinity of a supermassive black hole. Ghez and Genzel shared the Nobel Prize in Physics in 2020, together with Roger Penrose, for the discovery of a compact supermassive object at the center of our galaxy. The prize citation noted the measurement of stellar orbits around the galactic center as the primary evidence for this object. The decades-long tracking of stars like S2, S38, and dozens of others, each tracing an elliptical orbit around the point mass at the galactic center, constitutes one of the most precisely executed astronomical programs of the modern era, requiring 3 decades of continuous observation with state-of-the-art instrumentation and the development of new techniques in astrometry and orbit determination. The future of galactic center astronomy includes the next generation of extremely large telescopes. The Extremely Large Telescope under construction in Chile, with its 39-meter mirror, and the Giant Magellan Telescope, also in Chile, that will extend the galactic center observations to fainter stars closer to the event horizon with even higher precision. These observations will test general relativity in new regimes, constrain extensions of general relativity that predict deviations from the Kerr metric, and possibly detect relativistic effects in the orbits of stars close enough to the black hole that quantum gravity effects, while still tiny, might in principle leave a trace. The prospect of detecting quantum gravity effects in the orbits of stars near Sagittarius. A star is extremely remote. The quantum gravitational corrections to the classical orbits are fantastically small, far beyond the measurement precision of any foreseeable instrument, but the principle is important. The galactic center is the nearest laboratory for strong field gravity, and every improvement in the precision of observations, there is a step toward the regime where quantum gravity becomes observable. The steps are small, but the direction is clear. The theoretical landscape of black hole physics in the early 21st century is populated by ideas of extraordinary range and ambition, many of them too recent and too speculative to be placed in the settled account of what we know, but too interesting and too well developed to be dismissed. Among the most striking of these is the complexity equals action conjecture, proposed by Adam Brown and collaborators, which relates the computational complexity of the quantum state of a black hole. Essentially, how many elementary quantum operations would be required to prepare the state from a simple reference state to the volume of the Wheeler-DeWitt patch of the black hole's interior, which grows linearly with time. The conjecture, if correct, would mean that the interior volume of a black hole is a physical quantity with a precise quantum mechanical meaning, the complexity of the holographic boundary state, and would provide a new connection between geometric and information theoretic concepts in quantum gravity. The growth of complexity with time inside the black hole in this picture would continue long after the Bekenstein-Hawking entropy has reached its maximum value. The complexity would continue to grow for times exponentially longer than the evaporation time, reaching its maximum only when the black hole has been completely evaporated and the full complexity of the initial state has been processed. This timescale, exponentially longer than the age of the universe, is associated in quantum gravity with the recurrence time, the time after which a quantum system returns arbitrarily close to its initial state, and it connects the physics of black holes to the deepest properties of quantum mechanical time evolution. The concept of complexity, borrowed from theoretical computer science and quantum information theory, has become a tool for probing aspects of black hole physics that entropy and entanglement alone cannot capture. Where entropy measures the number of possible microscopic states consistent with a macroscopic configuration, and entanglement measures the quantum correlations between different parts of a system, complexity measures how hard it is to create a given state, how long the computation would take, how many steps would be required, how far the state is from a simple reference state. The application of complexity to black hole physics is a sign of how deeply quantum information concepts have penetrated the field, and how the questions raised by black holes are driving the development of new mathematical tools. The related concept of quantum error correction, the techniques developed for quantum computers to protect quantum information from decoherence and errors, has been found to play a deep role in the holographic encoding of bulk physics in the boundary theory. The work of Ahmed Almheri, Shi Dong, and Daniel Harlow on holographic quantum error correction showed that the encoding of bulk operators in terms of boundary operators has the structure of a quantum error correcting code. Bulk information is redundantly encoded across many boundary degrees of freedom, so that the loss of any small fraction of the boundary does not destroy the encoded bulk information. This result has a striking implication for the black hole information paradox. If the encoding of the black hole interior in the Hawking radiation has the structure of a quantum error-correcting code, then the information about the interior is protected from the loss of any small fraction of the radiation, and extracting it requires access to a large fraction of the total emitted radiation. This provides a concrete picture of how information can be preserved in the Hawking radiation without being immediately accessible from small samples of the radiation, consistent with the observation that the Hawking radiation appears thermal when only small samples are examined, even though the full radiation contains all the information. The future of black hole physics will be shaped by the interplay between theory and observation in ways that are only beginning to become clear. On the observational side, the growing catalogue of gravitational wave detections will provide detailed population statistics for black holes, their mass distribution, their spin distribution, their merger rate as a function of redshift, that will constrain models of stellar evolution, galaxy formation, and the origin of the most massive black holes. The detection of intermediate mass black holes, objects in the mass range between stellar mass and supermassive, roughly between 100 and 100,000 solar masses, would fill a gap in the black hole mass function whose existence is predicted by some formation mechanisms and whose absence would constrain others. The Laser Interferometer Space Antenna, LISA, scheduled for launch in the early 2030s, will detect gravitational waves from sources that are inaccessible to ground-based detectors because of their low frequencies. Sources including the in-spiral of stellar mass compact objects into supermassive black holes, the mergers of supermassive black holes, and possibly the stochastic background of gravitational waves from the early universe. The extreme mass ratio in spirals that LISA will detect will trace thousands of orbits around the central black hole before final merger, mapping the space-time geometry of the black hole with extraordinary precision and providing tests of the Kerr hypothesis, the prediction of general relativity that black holes are described by the Kerr metric, at a level of precision that will either confirm the theory or reveal deviations that require new physics. The pulsar timing array programs, which use the extremely regular pulses of millisecond pulsars as a galaxy-scale gravitational wave detector, have recently announced evidence for a stochastic gravitational wave background at nanohertz frequencies, the frequency range expected for gravitational waves from merging supermassive black hole binaries. The North American Nanohertz Observatory for Gravitational Waves, the European Pulsar Timing Array, the Parkes Pulsar Timing Array in Australia, and the Indian Pulsar Timing Array have all reported consistent signals that are interpreted as the superposition of gravitational waves from the enormous population of supermassive black hole binaries throughout the universe. If confirmed and characterized in more detail, this background would provide the first direct evidence for the population of supermassive black hole binaries, the precursors to the supermassive black hole mergers that produce the most energetic gravitational wave events in the observable universe, and would constrain models of how supermassive black holes grow and merge throughout cosmic history. The pulsar timing array background is the low-frequency complement to the high-frequency detections of LIGO and Virgo, covering the mass range from millions to billions of solar masses that ground-based detectors cannot access. On the theoretical side, the development of quantum gravity will be driven by the internal tensions within the field, the incompatibility between general relativity and quantum mechanics, the information paradox, the nature of the singularity, as well as by the new constraints provided by observation. The resolution of the firewall controversy, if it comes, will require either a modification of quantum mechanics, a modification of general relativity, or a new understanding of the relationship between space-time and quantum information that transcends both. Any of these would represent a fundamental advance in physics comparable to the development of quantum mechanics itself or the formulation of general relativity. The development of quantum computing, which is proceeding rapidly and which will eventually produce systems capable of simulating the quantum dynamics of complex systems that are intractable for classical computers, may play an unexpected role in the study of black hole physics. The SYK model and related exactly solvable models of holographic quantum gravity are complex enough that their full quantum dynamics cannot be simulated on classical computers for large system sizes, but they may be within reach of near-term quantum computers. Simulating the quantum dynamics of these models would allow researchers to study the spreading of quantum information, the growth of entanglement, the onset of quantum chaos, and the properties of the Page curve, the curve that describes how the entanglement entropy of the Hawking radiation changes over the lifetime of the evaporating black hole, in ways that go beyond what analytical calculations alone can reveal. There is a kind of vertigo that comes from thinking seriously about the scale of all this. You are a collection of approximately 7 billion atoms, arranged by evolution and development into a structure capable of generating the experience of lying in the dark and thinking about the universe. The atoms of your body were made in the interiors of stars that lived and died before the solar system formed, their material distributed through the galaxy by stellar winds and supernovae, eventually incorporated into the molecular cloud that collapsed to form the sun and the planets, eventually assembled by chemistry and biology into you, the black holes in our galaxy, the 40 million stellar mass remnants of dead massive stars, and the 4 million solar mass object at the galactic center are as much a part of the history of the atoms in your body as the stars that made those atoms. The supernovae that produced many of the stellar mass black holes also produced and distributed the iron in your blood, the calcium in your bones, the carbon in your DNA. The galaxy in which all of this happened was shaped partly by the activity of the supermassive black hole at its center, which regulated star formation over billions of years, maintaining the conditions under which solar-type stars could form and solar systems like ours could develop. You are not merely observing the universe, you are, in a specific and literal sense, the universe observing itself, a local configuration of matter that has developed the capacity to study and understand the physical processes that produced it. The physics of black holes is not a separate subject from the story of your existence. It is part of that story, as much as the chemistry of DNA or the evolution of the nervous system. This is not a mystical statement, but a physical one. The causal chain from the Big Bang to your awareness of this sentence runs through the formation of stars, the nucleosynthesis of heavy elements, the supernovae that produced them, the accretion disk physics of the young sun, the geochemistry of the early Earth, the chemistry of the first self-replicating molecules, the long evolution of life, the development of nervous systems, the cultural history that produced the language in which this is written, and the specific circumstances that led to your reading it. Black holes are not incidental to this chain. The regulation of star formation by AGN feedback, the production of heavy elements in the supernova explosions that form black holes, the shaping of the galaxy's structure by its central black hole. All of this is part of the physical context in which you exist. Sleep is approaching. The thoughts are slowing. The narrative of the day is losing its urgency. The specific concerns and memories and plans of the waking hours dissolving into the more general awareness that precedes sleep. The brain is transitioning, the adenosine building up, the arousal systems quieting, the default mode network taking over the processing of the day's accumulated experience. And somewhere in the Milky Way, at a distance of 27,000 light-years, the black hole at the galactic center is doing what it does, which is very little at the moment in its current quiescent state, but which is still the gravitational shaping of the galactic center region. the slow capture of any gas cloud that wanders too close, the bending of the space-time in which the nearest stars trace their orbits at thousands of kilometers per second. The light from those stars, the infrared light that Guer's and Genzel's instruments have been collecting for 30 years, left the galactic center 27,000 years ago. Whatever those stars are doing now, at this moment, you will not know for another 27,000 years. The universe is not designed for immediacy. It operates on timescales that dwarf the entire history of human civilization, communicating across distances that make every human journey seem infinitesimal, maintaining processes, the long, slow evaporation of black holes by Hawking radiation, the gradual cooling of the universe, the inspiral of binary systems toward their eventual merger, that will continue for times beyond any meaningful comprehension. Against these timescales, the length of a human life is not even a rounding error. It is less than a microsecond in the lifetime of a stellar mass black hole. It is less than a nanosecond in the timescale of Hawking evaporation for a black hole of even modest mass. And yet the entire scientific understanding of black holes described in this account, from Michel's 1783 calculation to the first gravitational wave detection in 2015 to the current state of the information paradox debate, was produced in that less than a microsecond of cosmic time. The pace of human understanding is extraordinary relative to the pace of the cosmic processes it describes. In the time it takes a stellar mass black hole to evaporate by a fraction too small to measure, human science has gone from knowing nothing about black holes to imaging their event horizons, detecting their mergers, and grappling with the quantum mechanical paradoxes they generate. That pace will continue. The next generation of telescopes and detectors will see things that cannot currently be anticipated. The next generation of theorists will formulate ideas that current understanding does not provide the vocabulary to describe. The question of what happens at the singularity will be answered, or replaced by a better question, or shown to be the wrong question, which itself would be a kind of answer. The recognition that the singularity, as described by classical general relativity, is not a physical place at all, but a mathematical artifact of an approximation that breaks down before the extreme conditions are fully reached. The universe will keep its secrets as long as the understanding required to unlock them has not been developed, and the understanding will be developed, slowly, unevenly, with wrong turns and corrections, and the occasional flash of insight that reframes everything that came before. This is the nature of scientific knowledge, and the history of black hole physics is one of the clearest illustrations of how that knowledge develops. From initial prediction, to skepticism, to confirmation, to the revelation of deeper mysteries that the confirmation uncovers. You are on the edge of sleep in a universe that is still being understood. The understanding will continue. Through the night, through the years, through the generations of scientists who will come after, and will push the frontier further than it has been pushed before. The black holes will wait, patient as they have always been, for the understanding to reach them. Close your eyes. The universe is very large, and it is very old, and it is full of things that science is still learning to describe. The darkness around you is full of light that has traveled billions of years to reach this neighborhood of the cosmos. Light bent and redshifted and stretched by the expansion of the universe and by the gravitational fields of the objects it passed on its way. Gravitational waves from black hole mergers that happened before the Earth was formed are passing through you right now, stretching the space between your atoms by distances too small for any instrument to measure, carrying the signature of events in galaxies whose light will never reach us. The information that falls into a black hole may not be lost. It may be encoded in the Hawking radiation in a form so subtle that extracting it would require measuring every emitted particle with a precision beyond anything we can imagine. But the physics, as best we currently understand it, suggests that the information is there, carried in the quantum correlations between photons emitted across the entire lifetime of the evaporating black hole, each photon individually indistinguishable from random thermal noise, but the whole collection carrying, in the specific pattern of their correlations, the complete record of everything that ever fell in. Everything that falls in comes back eventually in some form, transformed beyond recognition, encoded in radiation so diffuse and so cold that no instrument will ever detect it. But there, according to the best understanding we have, the universe does not forget. It is only very, very slow to remember.